chatting. Beating AI to solving physics. Just chatting, learning dinosaur fanboys physics. Okay. So first we draw. 1 hour of drawing. That should be enough. Let me see if the bitrate is good. The bitrate is good. YouTube is good. YouTube is good. God's precious Roomba believes not in God. Okay. Okay, let's just draw something because it's time. Let's go with red. See what we're gonna draw today. Today I wanna draw something special. Okay. And we're gonna fill the colors in. Which was the stupidest way to do it, but you know, who cares? Just a thing at the bottom of the ocean. Alright. Maybe a bit different that one. This is the perfection. Okay, we go green. This green. We draw. Okay. And we color it in. Perfection. Now we draw the pinnacle of human suffering and misery. Misunthresia. Say hi if you see me. This is 1 hour to get my brain ready for streaming. Okay. I guess it goes like this. Okay, and a bit of red, which will be the spires. Beautiful. And we color that in. Boop, 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 boop. All of it. Beautiful. Beautiful. Black. And that should be black as well. Doesn't matter. We can correct it as such. Here we correct it. Correct it. Correct it. And of course we have some pads. That pad does not look good. No. Nopey. Okay. We get our coloring and we fix it all. Beautiful. Now let's put a bright flame on a rocket. Oh, okay. And we have beautiful. Why does it do that? No. Oh, God damn it. Okay. Again, this is Mizantreshia, the city of Mizantresh. Okay. To space and beyond. Mizantresh. How does it float, you might ask? That's top secret. Top secret. C correct. Okay, but we have that image, and now we can save it as Misonthrascia, and we can get off to do some actual work. In journal, physics day 3. Okay, let's go. We ended it somewhere here. Motion in a plane polar coordinates. Rectangular or Cartesian coordinates are well suited to describing motion in a straight line. For instance, if you orient a coordinate system so that it exercises a motion, then only a single coordinate changes the point it moves. However, recording rectangular coordinates are not useful for describing circular motion. And since circular motion plays a prominent role in physics, it is worth introducing coordinates more natural to it. We should mention the older coordinate system we like. Okay. Okay, we understand coordinates. We understand them. I hope we understand them. Okay. Okay, we understand them. Put this there. Put this here. Okay. Okay. Polar coordinates, velocity of bead on a spoke. Okay. A bead moves along the spoke to a wheel at a constant speed u meters per second. The wheel rotates with uniform angular velocity theta equals theta radians per second about an axis fixed in space. At t equals 0, the spoke is along the z-axis and the bead is at the origin. Find the velocity at time t in a polar coordinates in Cartesian coordinates. We have r is equal to ut, r differential r is equal to u, theta is equal to omega. Hence, v is equal to theta due to differential r times r plus r theta theta differential is equal to ur differential equals ut omega omega differential. To specify the velocity completely, we need to know the direction of r and theta. This is obtained. Okay, the Cartesian coordinates we have v cosine sine. Okay, we obtain that. We obtain that. Not multiple in result in polar coordinates. True. 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 But what have we gained here? Okay. Approximation methods. We know that. Taylor series, I know that. Differentials. Consider a function. Okay, differentials is well understood by us. I know you guys know everything, so yeah, some references to calculus tests. No, not needed. Problems. Okay. Okay, let's do 3 random problems. And since we're doing 3 random problems, we are gonna use the number 3. So we are gonna use 1.21, 1.18, and 1.16, I guess. Okay. Why 1.16? A sports car, Fiasco 1, can accelerate uniformly to up to 120 miles an hour in 30 seconds. Jesus Christ, I need to convert miles. In maximum braking rate cannot exceed 0.7 Gs. So that's the maximum brake. What is the minimum time required to go half a mile, assuming it begins and ends at rest? Hint, the graph of velocity versus time can be helpful. So, what we are assuming here is, so it can go 120 miles per hour in 30 seconds. Okay, and then it needs to decelerate by this amount. So brake. So the braking acceleration is something like this, and acceleration is something like this, right? If this is the change of velocity per, and this would be the maximum 120 miles an hour. This would be 0. This would be 0. So something like that, I would imagine. 0.7 Gs. This is half a mile. Half a mile. Okay. Okay. So V is equal to A times T here. And we have the T. What else is it? What is the minimum required time to go to one mile, assuming it begins and ends at rest? Minimum to go half a mile. Okay, so it will not look like this. This is its top speed. This is its top speed. What we need to assume then is that 0.7 G that is the deceleration. That is the maximum breakage. So it should only depend upon that, I think, because I don't see any other way how it would depend on anything else, because this is only to get us what is the maximum time to minimum time required for that. So the minimum time required for 1 mile would be somewhere here. It starts breaking and goes there. So we have X and Y. What? 1.5 miles. X and Y. Is it gonna passing accelerate uniformly to that? Right. So maybe it looks like this. Right. All right, but it could look like this as well. It all depends on these three z. So z plus y is plus x is equal to 1.5 miles. Z is inverted z is inverted x. Okay, we know that. Z is not inverted x. It doesn't have to be. Z is not inverted x, but something is there hiding. And that is, so this is A, where A is 30 seconds, up to 30 seconds. It doesn't need to be 30 seconds. 1.5 miles. X plus Z. X plus. Okay. So we are looking for a minimum time. Okay, so we are looking for the min of A1 times T1 plus V uh, 1 V stable times T2 plus A2 times TX. Okay. A1 T1 plus VS TS TS is equal to plus A2 T3 2. Okay. So first let's see if this term matters at all. And to see if that term matters at all, we're gonna see where is it gonna be where it reaches the maximum velocity. And that is miles per hour. I can convert that. Luckily, miles per hour divided by times divided by 3 uh, 60 is 2 miles a minute, and another 60 is 1 in 30. 2 divided by 60. 2 divided by 60 is almost 3. 2.7 something. 2.7. not 2.7. 2.20. That's 80. That's 20 again. No. That's 300. 6. 2.26. 2.6 miles 0.2.6 miles per second. Okay, that's wrong, but okay. 0.26 miles a second. I'm gonna in 30 seconds. That's gonna be 120 miles an hour times 30. 20 hour times 30 divided by 360. 3 and a 3, 1 and a 2, 1, 12 and a 12, 100 and a 10. That's gonna be 0.1 miles. Okay. And it's gonna last 30 seconds. Okay. We have gotten that part. Now we have to go from 120 miles per hour to the acceptable zero via 0.7 Gs. Okay. Conversion, I need the conversion for conversion miles to kilometers. 1.6. So 120 miles is around 200 kilometers per hour. Okay. This then with 0.7 Gs. How long does it take to zero? It takes AT to zero, which is V equals T. 200 divided by 0.7 is equal to T. G is Newton. Me. This is kilometers per second, hour. 200, then we have an hour here, but we need a second here. 200 divided by 360 kilometers per sec times 1,000, so it's meters per second. 0.7 or 7 tenths meters per second squared is equal to T. This crosses, 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 crosses. Ook, ook. 36 times 7 divided by 20 times 10. Okay. And this is closer to 190.3. 190.3. 190.3. Which is calculator. I didn't think I would need to use a calculator. This is physics. Times 7 divided by 1.19.3 divided by 10. 1.3 seconds. Okay. So takes us 30 seconds to reach 120, and takes us 1.3 seconds to reach 1.3. Why times 20? Why times 20? Where is the 20? Where is the 20? 20, 20, 20, 20. I just converted this kilometers, 1,000. No, it's 1,000, not just 1,000. It's 1 second. Let me redo the calculation. You're right. Okay, let's redo the calculation. So 193.1 kilometers per hour divided by 7/10 meters per second squared, right? And also, I don't know why I typed kilogram here. Not really kilogram here. Okay. This is divided by 360 to get seconds, and times 1,000 to get the so we cross this 10 multiplies this 10, so it's 193.1 times 100 because of this 10 and this 10 divided by 36 times 7, right? That should be correct. And that's 193.1 times 100 divided by 36 divided by 7. 76 seconds. Okay, and that makes much more sense. So it takes 76 seconds and it takes 30 seconds to get to 120. And it takes 20 to get below 120 to 0. Okay, but what distance has it traveled? Let me see. The first time it traveled 0.1 miles. 0.1 miles. The second time it traveled, x is equal to 1.5 at squared. So the x is equal to 1.5 of 76 seconds squared. G is m divided by seconds squared. This cancels out, and a is 0.7. Okay, x is equal to, but it will give me in meters this time. We will convert miles later. So it will be 1.5, 0.5 times 0.7 times 76 times 76. This is meters. So 2061 meters. Something seems off. Something seems terribly off. Okay? And 1.5 miles, 1.5 miles, that's 160 meters. So that's then 2000 and 221 meters. Okay, how much is 0.5 miles? It's very little. It is not this much. So we do the other calculation. So it's like this, meaning we will not reach 120. We will start braking earlier. Okay, that is A1T plus T1 A G T2, and we know these quantities. These quantities we know. This quantity, no. We know these quantities. We don't know these quantities. We don't know time. Okay. T2 plus T1. We are minimizing for that. Okay. So let me just find A in G's. A1 is equal to 120 120 divided by 30. This is in miles per hour. Miles per hour, and this is in seconds. So A1 is equal to miles. We already said it's something insane, so I'm just gonna put a constant here. 1.6 times 1.6 divided by 360 divided by 30 divided by 1. Okay. A1 is equal to 120 times 1.6 times 1000 times 1000. I should say that times 1000 divided by 36 by 360 divided by 30. 1.7 Gs. Okay. So it's 1.7 Gs times T1 plus 0.7 Gs times T2. Okay. This on a graph looks like this, and then this with a longer T2. T1. Okay. So now we can just say what is equal to V, and V is 1 mile, half a mile, 1.5 miles, divided by T1 plus T2 seconds. Okay, that's 0.5 times 1.609 times 1,000, which is, I'm gonna calculate that real quick. 0.5 times 1,000 times 1.609, 804 meters divided by T1 plus T2 seconds is equal to 1.7 Gs plus 0.7 Gs T1 T2. Okay, we can adjust this to be 804 meters divided by 1.7 plus 0.7 Gs is equal to T1 plus T2. T1 plus T2. Sorry. Okay, is equal to, we can factor the G's, so 1.7 T1s plus 0.7 T2s times G. T1 plus T2. Okay. 804 meters is equal, divided by G is equal to 1.7 T1s plus 0.7 T2s divided by T1 plus T2. Okay. $804 meters divided by 1G. This is total time this should be minimized. So when is this minimized? At 804 meters. This is minimized. Sorry, I just want to encircle you. Thank you. This is minimized by doing the min of this, which is which is we need another formula. And another formula we get by looking that oh, the T1 is equal to 1.7 divided by 0.7 T2, right? 1.7 divided by 0.7 is equal to 2.5. T1 is equal to 2.5 T2, or T2 is equal to T1 2.5. I think it's different, so I'm gonna, yeah. Okay. And now putting this, we get that 804 meters divided by g is equal to 1.7 1.7. This is not connected, so we get this, and that is T1 plus T2 is equal to 3.5 T1. T1 is equal to 804 meters divided by g, which is just meters per second squared, and this is seconds, and this goes down the way, this goes up, this goes that way, 3.5 goes here, and T1 is equal to, calculator, 804 divided by 3.5, 229 seconds. Which seems too much. I don't know. The braking is too slow. Or this is meters, is it? Meters. Maybe I fucked the units. But T U is equal to 3.5 2.29 seconds. Is that normal? 2.29 seconds. 120. If we just had the car racing, how fast would it be? And then slowing down, how fast would it be? Let's see. Let's see the average. Why not? The average should be somewhere in between. So the average would be The average would be 120 more per hour, which I hate. So we're gonna just say 200 kilometers per second per hour, or 200,000 divided by 3,600. 200 divided by 36. 5 meters per second. Meters per second. And the race is 800 meters. So the average speed would be way, way slower. Okay. Next question. Is there a solution? There are no solutions. Maybe in the end. The solutions here. Relativity. K. This is the index. Okay. I don't see it maybe in the start. Aha. Uh, Six. List of examples. Preface. Let's ask ChatGPT. It should be able to. Or here maybe. Can we go down, please? I said this was gonna be boring. Very boring. I used to know this. But miles per hour, that fucks me up. Alright. We put it somewhere here. Come on. Where is it? Where is it? Okay. ChatGPT. ChatGPT does it in feet. Okay, step 1. Convert units for consistency. Okay. How do we know that's the final velocity? Oh. We know because it was said that is the final velocity. No, it says it can. It says it can. No, this is wrong. Please use metric, and it says it can accelerate up to that. The coefficient using metric. Keep in mind that exporting can but it's capable, not that it accelerates to that speed. Okay. Maximum speed is that, yeah. Okay. Alright, that's 53 meters per second. Wow. Maximum acceleration is 6 meters per second. Okay. We do acceleration for 30 seconds. Does it say, did it say, 1 second, uniformly in 30 seconds, it can. Okay, I'm gonna just get to the next one. 118. 118. I think I understand it now. The rate of change of acceleration is sometimes known as the jerk. Find the direction and the magnitude of jerk for a particle moving in a circle of radius r at angular velocity v. Draw a vector diagram showing the instantaneous position, velocity, acceleration, and jerk. Oh boy. Because I don't know how to begin this first. I know it's just a derivative. But is it the derivative? Okay. We know that this is R, this is V. Okay. We have A tangential and A normal. Okay. That we know. Tangential to the circle in the direction perpendicular to A, and its magnitude is RV. Okay. But you just do the integral, the derivative. Okay. That's not too tough. Next. A tire rolls in a straight line without slipping. Its center moves with a constant speed v. A small pebble lodged in the tread of a tire touches the road at time t. Find the pebble's position, velocity, and acceleration as functions of time. Okay, we're gonna do this one instead. 1.19. This is probably not the best way to do these. Let me see, what do they do? Okay, chapter introduction, reaction, motion, Newton's laws and forces, applications of Newton's laws. Chapter 2, assignments. Problem set 1. Let's see problem set 1. Okay. 2 trains in a B and dimensional analysis. Why? What? Collaboration, but you're encouraged to freely discuss homework projects with students and teaching staff. You must write your solution completely in Do not seek your forbidden consulting solutions from previous years or from the web. Okay. These are the problems, I would imagine. But why just only 2 problems? Let me see if I got the good problem set. Assignments. The weekly problem sets are essential part of the course. Working through these problems is crucial to understanding material deeply. Many problem lists are acquired from the textbook. Readings, assignments, exams. PDF, okay. Okay, let's see it. Consider two trains moving in opposite directions on the same track. The train starts simultaneously from two towns, Aville and Beville, separated by distance d. Each train travels toward each other with a constant speed v. A B is initially located in the front of the train in Aville. So this is A, this is B. This is the B. The B travels with a V greater, V2 greater than V. Okay, towards B wheel. Then it encounters the second train, it instantaneously reverses direction until it encounters the first train, then reverses again. The B continues flying between these two until it is crushed between the trains impacting each other. The purpose of this problem is to compute the total distance flown by the B until it is crushed. Assume that the B is faster than the trains. There are at least two good ways to solve this problem. One is to compute the distance for each flight leg and sum the resulting series. There is also another way to solve the problem with very little calculation. You are to do it with both ways. Okay, let's think. Think. Okay. So the B is there. It travels here. The B is here. It travels here. The B is here. Travels here. The B is here. And it is crushed. Okay. We're gonna assume V2 is equal to 2V. Just so we're simple. Simple, let me, okay. The B travels they will crash at D half. We know that much. We know, uh, we know that D half times V is equal to here. We know that 2 D half. No, we don't know that. We know, let me, what is the first picture? So, the B starts moving. It will encounter the first train here. The first train, by this point, moving from B wheel, is traveling with a velocity, which is S over T. And that velocity is V. Okay. If the B is moving at 2V, it will come it will come different times. Fuck. It's not important when this will go. It's important with this. So the B will go its way, and let us imagine the B is traveling like so here, which is D half D divided by T. some time. This here, d, will be dt of b times t. So it will be v2 times t, and here it will be v times t. There they will meet. Both of these gives us a distance. Okay? And if the distance is 2 times greater, then they will meet at a third. At 2/3. Then we look backwards. And backwards at 1/3 is the second train, the one from A wheel. But they travel again, and again they meet at 2/3. But this one has moved here as well, at 1/3. So backwards they go here, 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 here until they crash. Okay. Okay, I think I understand it. So what we are finding is, find an expression for the distance d covered by the b after its nth encounter with the train. Define d not as the distance traveled during the first flight from A wheel towards the train to B wheel d1. The distance traveled by the b during the first trip from A wheel train sum the resulting series and to get the final answer. So the first trip is v2 divided by v1 times t. Okay, that is 2 times t, which is not what we want. We want 2/3 times t. That's what we are seeing here. Let me express this in mathematical form. So the d is v squared times t plus v squared times t. No, d1 is equal to d minus d naught minus t plus minus sorry, plus v of t, right? So if this is 2/3 and this is 1/3, then we get then we here have 2/3 again. So d1, d2 is equal to d2 minus v2 t plus vt, but this time it changes because the whole d is not this anymore. It is a half of it. It's not a half of it. It's divided by v of t divided by proportions. So this one we have, it meets somewhere there. That's some x or y. That is this. Okay? That's some x or y. Now we need d2 to be equal to d1, which is this. This is d1. Minus this part again. So minus twice that. Right? Minus d naught x of y or I guess minus v of t. So it's here, x of y. And then again, minus v2t plus vt, which cancels, giving me d2 is d1 minus vt. But it moved. That's not possible. d1. So right. So that is d1. That is the distance traveled by the bee for the first time it traveled. Now that bee switches its turn, but it only travels d naught minus 2x or d naught, right? Or minus 1 minus x y d naught. Right. Uh, Okay. So that's D1. But this is D1x. Okay. Okay, so first one, it would be this. D0 minus V2t plus Vt. Second term, D0 minus 1 minus 1d0 minus xy, which is just minus, this is in plus xy, so it's traveling xy. Yeah, it's traveling xy. Why would I do that? It's traveling. Is it traveling xy? It's traveling to 2xy. This is true. Like this part is true. But when it turns around, we need to find this distance first. We need to find this distance first. And this distance is simply 2x y or d1, which is this, minus d0 minus xy d0. Right. If we now do these terms, it's d0 minus d1, pardon, d1 minus d0 plus xy d0. Okay. Or d1. No, it's this one, right? Come on, Winter, you can help me. D0 minus V2t minus Vt. This is the B. This is the train. When it turns around, the train has moved already. It has moved. Meaning the distance is shorter. And it's shorter by 1 minus xy of d. Right? Of the last one. Okay. So, which is equal to, which is then minus V2t plus Vt. Right. That is the second path. Now the third path. We can write this as d1 minus 1 minus x over y d0. d0 minus v2t plus vt. Okay. And this is the second chunk. This is the second chunk. The second distance, because we are not, we should really rename this one to, this is the first chunk, d1. d1 is equal to this. The second chunk is equal to this, okay? Okay. And x over y is equal to v2 over v1. So it simplifies to d1, which d1 is simply d0 d0 sorry, d0 minus v2t minus vt minus v2t minus plus vt, right? That is d minus 1 minus v2 over v d0 minus v2t plus v2t. Okay, then the next path. So we had this path, xy. We had this path to the xy. Then it found this xy. And we know the distance of this one. And we know the distance of this one. Now we need to know the distance of this one. This one has a distance of d3 or 2 minus 1 minus v2 or d1, right? d1 minus v2t plus vt, where this is d2 d2. Okay. Okay. So we just copy this one again and again and again. What can we do here? So this becomes 2. This becomes 2. Okay. So then simply it is d0 minus v1 v2t plus v1t. And then the next term is plus d0 minus 2v2t plus vt minus 1 or 2 to me d1, which is again d0 d0 d0. Okay. The first flight. First trip to Beeville train. To the air train. Okay. Can you not? Thank you. Okay. The next term is plus d0 minus 3 v2 v2t plus v1 3t minus 1 v2 v1 d1. Okay, because it's d1, because it's d1, we need this. And d1 is that, so does it simplify things? It does not certainly simplify things. Oh, it does. Oh, it actually does simplify things. This is d0 minus v2t plus v1t. This is this. Okay. So if that is that, then we are just literally multiplying okay, this is d0, which is not that, which is literally just d0 minus v2t plus v1t times times 3 times 3 minus 2 minus v2t right. So this would be the formula for every single one of them. So let's try it on the first one. On the first one, it's d0 minus 1 second, just defined d0 as the difference relative to the first towards Beeville. Okay, if this is d0, then this is d0. Okay, just they want us to use this as d0. So if that is d0, okay, that's d0. D2 d1 is equal to d0 times 2 minus 1 minus v2 over v1 dt d0. No, that doesn't make sense. Wait a second. So d d0 is equal to d minus v2t plus v1t. That is d0. d1 is equal to d0. Then we need to chop off a bit at the end. So we need to chop this xy here. So to do that, we just do this twice, right? We just do this twice, which is minus v2t plus 2 v1t, right? We just chopped it. Or this. What is this? Yeah. Because we chop that part off out. And we just need to chop it. That means minus. That's it. That's the part. Have I done the pluses wrong? Let me see. D0 is equal to V2 traveling this way. T. Okay, we have done so wrongly. We need the plus. We did the plus is wrong. D0 is equal to V2t minus V1t. Okay. D01 is equal to this is just D and this is D. And if this is like proportion to D, that's it. Then this is V2t, right? Minus 2 V1t. Okay. D1 is equal to, well, we have D0 now. Should factor in somewhere. It does not. Should be like this, D plus. D0 plus. Because that's the next series. Plus, plus V2t, 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 V2t minus V1t. Okay. And D02 is equal to D0 plus V2t minus 2 V1t. Okay. D2 is equal then to okay. So we just add It's just, yeah, it's just adding like that. Okay, we see what ChatGPT has to say for the first answer. Second answer we will answer later. Boom. Okay. Two V D over two V U times V. Okay. 2V total distance U times dV. What? Let me understand this. Okay, so ChatGPT tells me the two trains moving toward each other, their relative speed is 2v because both are traveling at the speed u v opposite directions. The initial distance between is d, so the time until they meet is d divided by 2v. We agree that. Distance flown during each leg. First leg from A wheel to B wheel. B wheel starts at B starts at A wheel and flies towards B wheel with speed u. The time it takes to reach the train B wheel is the same time it takes for the trains to meet, which is t. Why would it be the same? No, but the speed of a B is greater. Okay. Okay. U times t. So if U times t, first leg, it's flying until the trains collide. The total time first leg is it takes trains to meet, which is this is not true. The distance B travels during the first leg is U times t. U divided by after cutting B will beam turns on and flies back to A. The time it takes B to fly back towards the train until is D divided by 2V. Because the relative speed of the B and the train hasn't changed, therefore the distance traveled by the B is usually the same as the first leg. ChatGPT, I'm pretty sure that's not true. Is it? No, that makes no sense. Because if we have this, the B travels and it gets here. Then it travels and it gets here. Then it travels, gets here. Then it travels, then it gets here. It's like this. D0 is equal to D D0 is equal to D minus VT. D minus VT. D is equal to V2 T plus V1 T. Okay? They are coming towards each other. They will collide somewhere. That is D. Now D1 is this. Or D0, sorry. So D0 is equal to D divided by V1T. Sorry. D0 is equal to D1, V1T minus D, which is a negative number. Should probably be D minus, yeah, D minus V1T. That's D0. But the next time it goes, it's dx0. And dx0 is d minus 2 v1t. Right? Right. So it's 2 v minus t. Okay. So the next time it goes, it's d is d minus 2 v1t is equal 2 v2t again plus v1t. Okay, makes sense. Makes perfect sense. This is now d1, and d1 is equal to d1 is equal to d minus 3 v1t. So it goes like this. D0 is equal to d minus v1t. D1 is equal to d minus v2t. v1t. v3t. D2 is equal to d minus 5 v1t. Right? Each time, each successive time, getting closer. What does ChatGPT say? Let's see if it gets a better one. So t is traveling t d by 2uv until the trains collide. The b speed is u, and it is flying for the entire duration until the trains meet. Yes. Yes. So it is flying for the entire duration of the trains meet. That's a simple way to look at it. So we just need to find how long will it take until the trains meet, and the trains will meet. I did read a bit, but yes, the trains will meet at t equals distance divided by double the u velocity. Is that true? Okay. Hmm. Okay. We tried. We failed. We go forwards. Okay. Next. Dimensional analysis. You can often derive the solution of a problem by considering the dimensions of the relevant variables, including all related fundamental constants, and match the dimensions of the quantity you want to determine. This is called dimensional analysis. It is a powerful approximate technique. It is the method to scale with different variables. The basic idea is to OK and constants C. Okay, and solve for the powers so the dimensions of both sides equations work out. Okay, derive an expression for the vibration frequency of a star of mass m and radius r if that vibration is caused by gravitational instabilities. Okay. Derive an expression for the drag force of a ball radius r and mass m moving with velocity v through a medium with mass and density v. We will not be doing this one. I know dimensional analysis. Okay. Let's read the next chapter. Okay. Okay, we understand that. So yeah, in this method, this would go all the way up to the point where we can say, so this is 3, this is 1, 1, 3, 5, 7, 9. This will go all the way up until it's until they collided, and they have collided at t equals that. Okay, and I would just take that time t of the collision, which is basically this, because to you it is the same as one thing moving with twice their velocity, and we can times it with the velocity of the b v2, which will give us the total. Right. And we should get the same d total for this as well, right? Because if we sum this, this d is, well, yeah, it just sums, constantly shrinking. Every single time it shrinks by 2 because of the last one, and you get, we can ask then a question, how much would it be at d5? And at d5 it will most certainly be 5d minus minus 1 plus 3 plus 5 plus 7 plus 9 v1t, right? And then we would get 1 and 7 to 25 v1t, right? Okay. And that's just, okay. F equals ma, Newton's third law, we know this. We should find somewhere standards and units. It's some applications of Newton's laws. This is not a good book. Everyday forces of physics. Okay, I know this. Let me try to find something more. So this is problem set 1. Let me see problem set 2. That was actually fun to do. Okay. Okay. Okay, we will do this. Remember. Assignments, readings, calendar, syllabus. Let us, why not go to youtube.com and be like 80012 MIT. Okay. We know this. No sound. Far. 1 second. No sound. Yeah, 1 second. Okay. Even I can barely hear it.
And now we can find the angle. The angle, the tangent of the angle, is just equal to the y component
Should
divided by
work
the x
now.
component, like this. And so in this way we can solve for the angle. Now let's practice going back the other way. If we're given a vector whose magnitude is 2 and whose angle from the x-axis is 30 degrees, like this one here, then the x component is just the magnitude times the cosine of the angle, so 2 times the cosine of 30, and the y component is just the magnitude times the sine of the angle, so 2 times the sine of 30.
Okay.
Now that we've chosen a coordinate system for our runner going along a road, we now want to describe the position function of that coordinate system with respect to our choice of origin. Now, the runner is a non-rigid object. Legs and arms are moving back and forth. So let's just imagine that there's some fixed point in the runner at the center, and let's give a vector. So we're going to point here has an x coordinate. So we can now introduce our position function, which we'll call x of t, which is the coordinate location with respect to. Now remember, this is a vector. The position function is just a quantity that's describing x of t, is what we call the component of the position vector. Remember, a vector has a component.
The volume is low. Okay. 1 second. Let me adjust it.
And the component is the position function. And that component, x of t, can be positive, as you see in this particular case. X of t can also be 0. That's if you're located at the origin. And if our runner's on the other side of the origin, x of t can be negative. So the component of the vector, of the position vector, can be positive, 0, or negative. And we'll now describe the position vector, because I don't want to overlap it. That center point is up here. It's going to point in this direction. And this is what we call r of t plus delta t. And that vector, r of t plus delta t, the coordinate function is no longer time t, but t plus delta t, I hat. And we would now like to describe the displacement vector. So our next step is to describe the displacement vector for the interval t to t plus. And that displacement vector is defined, we use the symbol delta r, and what we mean is the vector r of t plus delta t minus the vector r of t. Now what that vector corresponds to is the vector right here. This is our delta r. And if we now use our two definitions here, then this becomes x of t plus delta t minus x of t I hat. And this quantity here we refer to as the component of the displacement vector. So delta x is the component of the displacement vector. And as before, the component can be positive, which would correspond to the person moving a positive component, positive I-hat direction, in the positive x direction, as shown in this figure. If the displacement vector is 0, the person could have run forward and come back, and at time t plus delta t be in exactly the same spot as time t. The displacement vector is 0. In that case, the displacement vector could have a component that's negative, and what negative means is at the end of this interval, t plus delta t, that the person is on to the left of the runner. And so this quantity would be negative. And so this is our crucial displacement vector that describes only the difference between the person between time t plus delta t and time t. Now that we've described the displacement of our object, remember that our displacement vector delta r in this time interval was x of t plus t minus x of t I hat, which we denoted as delta x I hat.
Is it better
Let's just remind ourselves
now?
that this distance here, that's delta x, and this whole distance from here over to there, that's what we mean by x of t plus delta t.
I need to get
And now
more.
what we'd like to do is describe what we call average velocity. And our average velocity depends on our time interval. So this is for the time interval, t to t plus delta t, while the person has displaced a certain amount of vector delta r. And our definition for v average, it's a vector quantity, so we'll write v average. We'll use 3 bars to indicate a definition. It is the displacement during a time interval delta t. So as a vector, we have delta x over delta t I hat. And this component here is what we call the component of the average velocity. So this is the component of the average velocity. And again, as before, this component can be positive, 0, or negative, depending on the sign of delta x. And the key point here is that average velocity depends on whatever time interval you're referring to. So that's our definition of average velocity. And now what we want to do is consider what happens in the limit as delta t becomes smaller and smaller and smaller. And that will enable us to introduce our concept of instantaneous velocity.
Good. Okay. I will be skipping a
We now
lot.
described what we call the average velocity for a time interval between when the runner started at time t to a later time at t plus delta t. And we describe that as the component of the displacement vector divided by the time interval times a unit vector I hat. Now what we'd like to ask a separate question. So our question now is, what do we mean by the velocity at some specific time, t1? Now, in order to understand that, let's just make a plot of the position function. So remember, we called the component of the position function x of t. So we're going to plot the component of the position function with respect to time. Now, let's just say that the runner started at the origin of time equals 0, so I can make some type of arbitrary plot of that position function. And let's indicate in particular the time t1. So what this represents is x of t1. And so first I'd like to consider the interval t1 and t1 plus some later time delta t. So let's make this t1 plus delta t. This is the time delta t. And up here, we have our position function of t1 plus delta t. Then for this time interval, the average velocity, so for this particular time interval, the average represents delta x over delta t. So it's just the rise over run. It's just the slope of this straight line. So for this particular interval, the average is the slope of the line shown here on the figure. Now, this is just an average velocity, and now what we would like to do is shrink down our interval delta t. So now let's make another case where we shrink delta t, and let's again calculate the average velocity. So for instance, suppose we have a smaller delta t, and we draw that line. Then our average velocity represents that slope. And again, we keep on taking a limit. So now we have another slope. So we have one slope, two slopes, and now we shrink again to a new delta t. And you can see velocity at time t equals t1. And that's how we describe instantaneous velocity at some specific time. If we were now being a little bit more general, we could just say that v at any time t is the limit delta t goes to 0, delta x over delta t, all direction I hat. And the only thing here is we're no longer considering t1, but an arbitrary time t. This quantity, the limit, is awkward to write every time. It has a name, and that's precisely what we call the derivative of the position function. So our instantaneous velocity is the time derivative of the position function at any instant in time. Let's consider a one-dimensional motion that has a non-uniform acceleration. What we'd like to do is explore how do you differentiate position functions to get velocity functions to get acceleration functions. So what we're going to consider is a rocket. So I'm going to choose coordinate system y, and here's my rocket, and I have a function y of t, and I'll have a j-hat direction, but this will be a one-dimensional motion. Now, I want to express, while the rocket is thrusting upwards and the engine is burning, we can describe the function y of t to be equal to 1/2 constant a naught minus the gravitational acceleration times t squared. And we're going to have a separate term here, which is minus 1 over 30, and you'll see where this 30 comes in as we start to differentiate. Same constant a naught t to the 6th over t naught to the 4th. Now in this expression, a naught is bigger than g, and also this is only true, this holds for the time interval 0, less than or equal to t, less than t naught. And at time t equals to t naught, the engine shuts off, and at that moment, our expectation will be that the y component of the acceleration should just be minus g for t greater than t naught. So now let's calculate the acceleration as the velocity and the position as functions of time. So the velocity, in each case, we're going to use the polynomial rule. So the y component of the velocity is just a different derivative of t squared, which is just 2t. And so we get a naught minus g times t. And when we differentiate t to the 6th, the 6 over 30 gives us a factor 1 over 5. So we have minus 1 over 5 times a naught t to the 5th over t naught to the 4th. And this is a combination of a linear term and a term that is decreasing by this t to the 5th factor. And finally, we now take the next derivative, a y of t, which is d dy dt. I'll just keep functions of t, but we don't really need that. And when we differentiate here, we get a naught minus g. Now we see the 5's are canceling, and we have minus a naught t to the 4th over t naught to the 4th. Now, at time t equals t naught, what do we have? Well, ay at t equals t naught. This is just a factor of minus a naught, those cancel, and we get minus g, which is what we expected. we've described the instantaneous velocity of an object, we'd now like to describe what its acceleration is. Velocity and acceleration are complicated things. One of the reasons why acceleration is such an abstract quantity is, for example, if I take this marker that's in my hand and I throw it up in the air and I catch it, you can see with your eye velocity. You can see the speed, you have a sense for it, you can see it change its direction. So velocity is something that as a human being with our eye as a mechanism for determining motion, velocity is a very basic concept. But acceleration is a much harder concept. For instance, when I take that same object and I drop that, as it falls down, its velocity is increasing, and so we say it has an acceleration. But is that acceleration a function of time? Or is it constant in time? Is it varying in time? Is it a polynomial? Is it a constant? Those are much harder to see. Again, let's drop this object. So when I drop that object and I catch it down here, our eye does not tell us intuitively anything about the mathematical nature of that acceleration. And that's why acceleration is a much more abstract quantity. In fact, a great question is the following. When I throw this object up in the air, let's focus at its highest point. So I throw it in the air, and it comes down. When the object was at its highest point, was its velocity 0? Was its acceleration 0 or non-zero? A hint to this question is in Newton's second law, F equals ma. If there's a force acting on this object, there must be an acceleration, and that force is the gravitational force. And when this object was at the top of its motion, I didn't turn the Earth off. So there's still a gravitational force. And so for an object in free fall, now free fall just is which means under the influence of the gravitational force,
There is always an acceleration.
we can conclude from Newton's second law that the gravitational force, ma, so this
But the
gravitational force
velocity was
is
0
non-zero,
at the
and
top.
so therefore the acceleration is also non-zero. So once again, as I throw this object up in the air, nobody turned gravity off, we're not in empty space, and near the surface of the Earth, the gravitational force is not zero, the acceleration is not zero. So throughout this motion, this object is accelerating. I choose this example to show you that acceleration is a very abstract concept, and now our goal is to figure out how to mathematically define acceleration in terms of our velocity. We now describe what we call the instantaneous velocity at some time t. And we talked about it as a limit, as delta t goes to 0, of the displacement over the time, which we wrote as the derivative of the position function in terms of I hat. Now, this derivative, we're going to use a notation. We'll just write that as v of t I hat, where v of t is the component of the instantaneous velocity at time t. Now remember, this is just a symbol, but we describe this as the derivative of the position function, which I'll indicate as a function of time. And that's what we mean by the component of the instantaneous velocity. Now what we'd like to do is ask ourselves, how does the velocity change in time if the runner is increasing their velocity? Well, in general, we'll do exactly what we did before. What we'd like to introduce first is the concept of the change in the velocity, delta v, which we'll describe as the velocity at time intervals. I think
That's a limit, that's a...
slope a of t I hat, and that component a of t, the position.
Okay.
Let's consider a very simple example of a runner in which our position function, x of t, is given as a quadratic function in time. It will be a constant, b times t squared. Here, b is a constant. Now, it's always important in SI units to consider what the units of this constant is. Because the position function is measured in meters, and time is measured in seconds, b is a constant, and it has units of meters per second squared. And there's an example of a runner, and let's make a plot of that position function. So we're going to plot x of t as a function of time. B here, let's make b a positive constant, and so our function looks something like that. Now, the velocity, component of the velocity, remember v of t, is given by dx dt of this function. And the derivative of the polynomial t squared is very simple. That's just simply 2b times t. Again, let's look at our units. Because b has units of meters per second squared, and we're multiplying that by second, we have the units of velocity in SI units as meters per second. Now, let's plot that function. Notice this is a linear function. And so if I plotted underneath here, the velocity as a function of time, it starts off with a 0 slope. Remember, we're looking, our velocity at any given time corresponds to the slope of the tangent line to the position function. And you can see that slope is increasing. Now, you wouldn't know from this graph, but if you did plot t squared, it's increasing linearly. And so our velocity function, the initial slope is 0 at t equals 0, and it's increasing linearly in time. So we'll just draw that as some linear function. And the slope here of this function will be now the acceleration. So a of t is the derivative of the component of the velocity function as a function of time. And this derivative is quite easy. It's just simply 2b.
2.
Now notice those have the units of meters per second squared, which are our units for acceleration. When we again look at the slope, notice that at every single point, the slope of the velocity as a function of time is a constant. The slope here is just equal
Increases
to 2b.
by 2.
And so now, if we plotted our acceleration function, we have this point 2b, and every single point has the same value of acceleration. So here, the acceleration is an example of constant acceleration. And this is our simplest case. Notice we started with the position function, we differentiate to get the component of the velocity and to get the component of the acceleration. So this is a very simple model for a runner who's increasing speed linearly, accelerating at a constant rate.
If we know the position x of t of an object as a function of time, we can use differentiation to calculate its velocity and its acceleration at given times. Essentially, by taking the derivatives of the position, we know everything there is to know about the motion. Sometimes, however, we'll want to go in the other direction. We'll have the acceleration as a function of time, and we'll want to find the velocity as a function of time, or the position as a function of time. We'll use a technique called integration. The check b, we can a naught is just the time interval 0 to delta t, and it's the area of velocity at any later time. In this way, because the change isn't constant, but is. I can draw this graphically as well. Here's acceleration. This is time equals 0. Suppose the acceleration is just increasing linearly, and I'll call this time delta t. This is a of t. Note that we can define an average acceleration over the interval from 0 to delta t. the average acceleration is the change in velocity over the elapsed time. That average acceleration will look something like that. And so then the change in velocity, delta v, is equal to the average acceleration times the elapsed time. And this time, notice from the diagram, this product is actually the area of this trapezoid. That's basically the area under the a of t function going from 0 to delta t. We've calculated it sort of as a rectangular area involving the average acceleration, but that's also equal to the area under the time-changing acceleration function.
Yes.
So this is, again, the area under a of t over the time interval delta t. Now let's consider a more generally changing acceleration as a function of time. So let me plot this. So suppose we have just some general function, I'll draw it like this, which is our acceleration as a function of time. The change in velocity will still be the area under the curve a of t over the time interval we're interested in. So let's suppose we want to go from this time here, I'll call it t sub a, and my ending time will be t sub b. So we're interested in figuring out what the area under this curve is over the interval from t sub a to t sub b. We can estimate this by breaking up the interval into a bunch of little rectangles. Suppose I break this up into n rectangles, just under this curve.
Integration.
The change in velocity will do that interval. The change, and so we want the acceleration, call that. Now for a finite, I really should write this as approximately equal to, because for the rectangle, the better the approximate strip is equal to the limit of time as n, the number of rectangles, goes to infinity. It as the integral of the function a of t dt evaluated from time equals t sub a to time equals
T sub b.
we've written this way on the right, process of integration declaration from calculus. Let's begin by considering a function g of x with some derivative. So consider a function g of x, and let's assume it's a well-behaved function, by which I mean that it's continuous and differentiable over the interval that we're interested in. So consider g of x with the derivative, so dg dx equal to another function which I'll call f of x. Now, note that if I add a constant to g of x, I'll still get the same derivative. So note that the derivative with respect to x of g of x plus a constant is still equal to the same function f of x. And this is because the derivative of a constant is equal to 0. Now, suppose I want to invert this process. Then I can write that the antiderivative of f of x, the antiderivative, hand side of this we call an indefinite integral. X is like
Okay,
the integral of
integration.
x equals a. Okay? And so, just to see this graphically, if I plot my function f of x, and suppose this is x equals a, and this is x equals b, this definite integral represents the area
From a to b.
under the curve f of x in the interval from x equals a to x equals b. So calculus tells us how to solve this area problem, how to compute a definite integral from the antiderivative that you get from indefinite integration. And so this same technique tells us how to determine the velocity from the acceleration, since we saw that that was equivalent to an area under the curve problem. So to come back to the motion of objects, we've shown that the change in velocity of an object can be written as the definite integral of the acceleration. So just to write that a little bit more formally, first with a plot, if this is my acceleration as a function of time, we know that the time derivative of the velocity is equal to the acceleration as a function of time. I can rewrite that as the differential dv is equal to a of t times the differential dt. And so then I can integrate both sides of this equation by writing the integral over dv is equal to the integral of the acceleration a of t dt. And I can go from time equals some initial time t naught to time equal to some later time t sub 1 on the right-hand side to make a definite integral. And then on the left-hand side, the corresponding limits are the velocity at time 0, I'll call that v naught, and the velocity at time 1, which I'll call v1. So just to be clear, I'm assuming here that v naught is equal to the velocity at time of derivative of t in time t0 in terms of what the velocity is at some later time, t1, by writing the velocity at t1 is equal to v naught plus the integral of a of t dt from t equals t naught to t equals convenient way of writing 1 with an arbitrary time t. So I have that v of t is equal to v naught plus the integral of a of t dt from t equals t0 to t equals t. Now there's something funny here, because I have t in the integration variable here, but I have t as one of my limits here as well. Okay? Whereas if I look at this expression here, there's a difference between the t in the integration variable and the limit t1. They actually represent different things. So to keep track of that, the notation that we generally use in physics is to call this integration variable t prime. So we write this acceleration of t prime dt prime with the time t prime going from t naught to some later time t. Now one has to be cautious here. In some fields, that prime on a variable is used to denote a derivative, differentiation. That's not what it means here. I'm writing t prime just to distinguish it from the specific later time t that I want to calculate the velocity at. And it's worth thinking about what this expression means. This equation is identical to this earlier equation that we derived, except for a change in notation. And so let's think about what that notation means. T variable t prime, actually what I should do now is I should call this t prime. This variable t prime is taking every value from t naught to t. So t prime is representing the running time variable for all of our strips that we're adding up over this definite integral. Okay? So it's a placeholder variable. We sometimes call it a dummy variable. It's just a placeholder to represent time velocity. Just integrate equal to the position prime from acceleration. By integrating a second time, we can go from velocity to position. So once we know the acceleration a of t, we can use integration to compute the velocity v of t if we know the velocity at some initial time t naught, and we can also compute the position x of t if we know the initial position at time t naught x naught. So we see that given the acceleration, we can recover the velocity and position, and as it happens from Newton's second law, if we know the forces acting on an object, that gives us the ability to compute what the acceleration is, and then given the acceleration, we can use integration to find the velocity and the position.
Okay.
Let's consider a two-dimensional motion. Suppose we have something like projectile motion, and we have an object moving. Let's now describe how we can describe this motion with vectors. So the first thing we always want to do, and let's remind ourselves of the steps, is we want to choose a coordinate system. Now, what does a coordinate system consist of? It consists of an origin. It consists of two axes. In this case, we'll identify these, the positive direction for each axis is plus x and plus y. And at every single point in space, so if we had any arbitrary point p, here, p, let's call this p1, we have a choice of unit vectors I hat 1 and j hat 1. Now, what makes Cartesian coordinates unique is that no matter what point we're at, the unit vectors are all the same. So we could erase all these indices for that particular point and just have an abstract set of unit vectors I hat and j hat. Now, normally what we'll do is we'll just put those off to the side. So in our Cartesian coordinates, we now want to define the position vector. And the position vector is a vector from the origin to where the object is. So we'll write that position vector. We'll denote it by r of t, because as this object moves along its trajectory, that position vector is changing. And we'll write down r of t in terms of two coordinate functions, x of t and y of t. And so our vector, position vector of the object, r of t, is equal to x of t I hat plus y of t j hat. And one of our main goals is to figure out what these position functions are for the motion of objects. So this is how we describe an object in a Cartesian coordinate system undergoing two-dimensional motion. What we want to analyze next is what is the velocity of that object. Recall when we were examining the motion of an object in two dimensions, we introduced Cartesian coordinate and position vector. Now let's suppose the object has moved to a new point along orbit. Well, we'll write another vector, r of t, and let's say this took a time delta t to the new point. And what we want to define is the displacement of that object. So that's a vector delta r. And recall that a vector at time at t plus delta t is equal to the old vector r of t plus this displacement vector delta r. Now, what we want to consider is a limit as delta t goes to 0. And let's just look graphically at what that means. As we move this delta t, as delta t gets smaller and smaller, and our object is getting closer and closer to its position at time t, and the position vector r t plus delta t is getting closer and closer to r t delta t, the key fact is that if we do a tangent to the orbit, then the limit of delta r is approaching tangent to the curve. So in the limit delta r, the direction is tangent to the orbit. So that's our first key property of delta r. Now the second thing we want to express is if we write delta r as a displacement in the I hat direction and a displacement in the j hat direction. Now again, maybe we can just clean this up a little bit and see what we mean by that. So here's our delta r, and we have a little delta x in this direction, delta y in that direction. Remember, delta x or delta y can be positive or negative. That's all right. Now, if we want to define our velocity as the limit as delta t goes to 0 of delta r over delta t, then what we see is we have two pieces, the limit as delta t goes to 0 of delta x over delta t I hat, plus the limit as delta t goes to 0 of delta y, delta t, j hat. And the definition of these limits, we'll write that as the derivative dr dt. So the velocity is dr dt, and that's equal to the x dt, that coordinate function is changing in time, I hat, plus dy
dry
j hat. Now, as far as notation goes, we write this velocity as an x component of the velocity plus a y component of the velocity, where the x component, vx, is dx dt, and the y component is dy dt. Now, recall that the direction was tangent to the curve, but the magnitude of the velocity, what we call the speed, is just the sum of the squares of the components, the square root. And so now we've described what we refer to as the instantaneous velocity. So far, we've looked at a trajectory in two dimensions. Let's again consider some type of motion where we choose a positive y-axis, a positive x-axis, an origin, unit vectors, I hat and j hat, and we'll have some type of trajectory where our object is moving like that. We know that at this particular time, the velocity is tangent to this trajectory at that point. And now what we'd like to do is try to describe, we've described its two components, dx and dy, as a vector. So if we did vector decomposition, we would write a vector like this and a vector like that. This is the x component, that's the y component. And now if I define this angle theta, we know that a vector has a direction and a magnitude. We've seen that we call the magnitude the speed. So that's just the sum of these components, square root. Speed is always positive, so we always take the positive square root. And now what about the direction of this vector in the xy plane? Well, we can see from our geometry that the tangent theta is given by the y component over the x component. Or one could say that the angle theta at this given time is the inverse function of dy over dx. And so now we've described not only the direction of the velocity, but the angle that it's making with the horizontal axis. And so we've now completely described the velocity, instantaneous velocity vector at time t in terms of its two component functions, its speed, and the angle that makes the positive x-axis.
Makes sense.
Let's now consider two-dimensional motion, and let's try to analyze how to describe the change in velocity. So again, let's choose a coordinate system. We have an origin, plus y, plus x, and let's draw the trajectory of our object. And now let's draw the object at two different times. So for instance, if I call this the location at time t1, and a little bit later here, this is the location of the object at time t2. We'll call our unit vectors I hat and j hat. Now, we know that the direction of the velocity is tangent to this curve. So if we draw v at time t1, and over here, notice the direction has changed, v at time t2. And what we'd like to do now is describe, just as before, that our acceleration, a of t, is the derivative of the velocity as a function of time. What that means is the limit as delta t goes to 0 of delta v over delta t. Now, it's much harder to visualize the delta v in this drawing. And partly the reason for that is these velocity vectors are located at two different points. And right now, they're the backs of these vectors at different places in space. But remember that delta v is just v, in this case, at time t2, minus v at time t1. And our principle for subtracting two vectors at different locations in space is to draw the vectors where we put the tails at the same location. So here's the tail of this vector. We're just going to translate that vector in space. That is still v at time t1. These vectors are equal. They have the same length, and they have the same direction. And so delta v is just the vector that connects here to there. That's what we mean by delta v. And so you can see in this particular case that it's not obvious from looking at the orbit what the delta v is. So what we need to do is just trust our calculus. And so when we write the velocity as dx dt I hat plus dy dt j hat, and we're now treating each direction independently, we call this vx I hat plus dy j hat. So that's our velocity vector. Then our acceleration is just the derivative of the velocity. We take each direction separately, so we have dvx dt I hat plus dvy dt j hat. Now, again, notice that velocity v of x is already the first derivative of the position of the x component function. So what we really have here is the second derivative of the position function in the I hat direction, and the second derivative of the component function in the y direction, and that is what we call the instantaneous acceleration. Now, again, this is sometimes awkward to draw, but you always must remember that this x component of the acceleration, by definition, is the second derivative of the component function, or the first derivative of the component function for the velocity, and likewise, the y component of the acceleration, ay, is the second derivative of the component function for position, and that's also equal, by definition, to the first derivative of the component of the velocity vector. And that's how we describe the accelerate, squared, added together, taken square root, and that's our magnitude. And so now we've described all of our kinematic quantities in two dimensions: the position, the velocity as the derivative of the position, and the acceleration as the derivative of the velocity, where each direction is treated independently. One of the most common motions we see in our everyday lives is the path of an object moving, thrown, and moving through space. Now, this type of motion has a very famous name called projectile motion. And when we look at it, let's introduce a coordinate system, I hat and j hat. Here's our y plus y axis and our plus x axis. Then, in order to understand kinematics of this motion, we'd like to apply Newton's second law. So separately, we'll draw our object. It has gravitational force acting downward. Remember, our unit vector is in the j hat direction. And so when we write our equations of motion, F equals ma, we have two different directions. In the j hat direction, we have the gravitational force downward, minus mg. And remember here that g is our positive quantity, 9.8 meters per second. And we have MAY. Newton's second law equates these two different things, and that's, we'll write it like that. So those two quantities are equal. And so our conclusion is that the acceleration is equal to minus g in the y direction. Now, likewise, keep in mind that we have our horizontal direction as well. And notice there, we're now assuming that there's no horizontal forces. In the real world, there can be all types of air resistances. But here, for the simplicity of this model, we have no horizontal forces. So we have 0 equals max. And so we have our separate equation, ax equals 0. Now, both of these equations are equations that we've already been working with in kinematics. Here, we have constant acceleration, and here we have 0 acceleration. So using the result that we had earlier from integration, we can write down the equations of motion in the y and the x directions. First, we'll write the velocity. Vy as a function of time is equal to some initial value. And because acceleration is negative, minus gt. You can test your integration technique to see that. And the position as a function of time, remember, is just some constant value. This is our constant y naught. And we have plus vy naught t minus 1/2 g t squared, again, doing integration. Now, the horizontal equation of motion, the x of t, because there's no acceleration in the horizontal direction, this is constant value, given by the initial value of the component of the velocity in the x direction. And the position, x of t, is then equal to some initial position plus vx naught t. And so those are our functions of time for the components of the velocity and the components of position. Now, for our particular example, it's much easier. Here we have x naught equal to 0. Notice that our object is starting at the origin. And so that tells us that x as a function of time is just vx naught t. I'm dropping the parentheses t. Remember, that's not a product, it's just a function of time. And given this fact, that tells us that t is x divided by vx naught. And now I can take this value of t and put it into our vertical equation, and I get vy is some initial value plus vy naught x over vx naught, substituting for t, minus 1/2 g x squared over vx naught squared. When we describe projectile motion, we had an equation describing y as a function of t, an equation describing x as a function of t, the horizontal motion, the vertical motion, and here we have a separate equation which is describing the y as a function of x. Notice there's no time involved in this equation. Now let's try to look at graphically what we're seeing here. So for instance, when we look at a plot of the motion of y versus x, we can see the vertical component going up and down, and we can see the horizontal component moving to the right, while the object is following this trajectory. And this is a parabolic trajectory of y as a function of x. Now, if we wanted to actually plot out y as a function of t, then here we can look at the simulation where we're just looking at the y component, and you can see that that motion too is a parabola. However, what's crucial to look at is that it's y as a function of t and not y as a function of x. Finally, we can look at the horizontal motion, and again recall that when we looked at the trajectory as y as a function of x, you can see the horizontal motion component. Let's plot that separately, x as a function of t. And when we make that plot, you can see that this is just a linear equation in time where there's some initial condition, x naught, and so that's
Until it
the
hits
plot
the ground.
of x as a function of t. And so we see three separate representations of this motion: y as a function of x, y as a function of t, and x as a function of t.
Okay. That is because it has the same velocity, and then it just moves the same.
I'd like to talk to you about solving these kinematics problems. So we're going to actually start by asking ourselves three separate questions anytime we start one of these kinematics problems, and this will help us really figure out what's happening in the motion. So the first question that we want to ask is how many objects are moving? So do we care about more than one object? And if we do, we need to make sure to label each one distinctively. We also want to know how many dimensions we need to care about for each object. The second question that we want to ask ourselves is how many stages of motion does each object have? So for example, if you're told that a bicycle is initially accelerating and then at a certain time it stops accelerating, then you know that that initial acceleration is going to have different equations of motion than the point in time where it now has an acceleration equal to 0. The final thing that we want to think about, we want to figure out what special conditions there are. So for example, you might be told that the cart is initially at rest. So what does that mean in reality? It means that you can write down something like v of 0 is equal to 0. That's what it means for the cart to initially be at rest. The cart is v at time 0 is equal to 0. So those are the kinds of special conditions that you need to pay attention for in the problem, and that will help you figure out, get all of the numbers or the variables that you need to solve your equation. Once you're done thinking through these different steps, the final thing you should always do before starting the problem is draw out your problem, properly label your system, and then of course draw your origin, your axes, and your unit vectors. And this way, it'll be easy for you to organize all of the different information that you have.
So in this example, we want to hit an apple that's hanging from a tree with a projectile. And the main point of the problem is to figure out at what angle to the ground should we aim our projectile when we fire it off in order to hit the apple. And in this example, we're assuming that the apple drops from the tree at the same instant that we fire the projectile. So in this drawing, which is put some dimensions in here, we'll assume that the apple starts out at a height h above the ground, that the horizontal distance from where the projectile starts to the apple is a distance d, that the projectile starts at a distance s above the ground, and that we fire the projectile off with an initial velocity v naught at an angle theta naught with respect to the horizontal. Okay? And let's define our origin to be right here on the ground, directly below where the projectile begins. We need to define our coordinate system, so the I hat direction will be horizontally to the right, and the j hat direction will be vertically upwards, okay, with an origin at this point. So the question that we have is, what should our angle theta naught be in order to hit the apple, which starts falling from the tree at the same instant that we fire our projectile, and we want to hit the apple before it hits the ground. Okay, so to work this out, we need to consider the kinematics of two separate objects, our projectile and the apple. So let's begin with the apple. So for our apple,
mg.
the apple drops vertically straight downward, so its horizontal position throughout its motion is just unchanged. So the x-coordinate of the apple as a function of time is just d, which is a constant. Its y-coordinate, it starts out at height h, and then it drops due to the acceleration of gravity, and so that's given by minus
G.
1/2 g t squared. It's minus because it's falling in the minus
Yep.
j hat direction. Now for our projectile, it's called a bullet. For our bullet, the x-coordinate of the bullet, it starts out at the origin at x equals 0, and its initial motion, it has an initial velocity v naught in this direction. The horizontal component of that is v naught times the cosine of theta naught, and so its displacement at time t is v naught t times the cosine of theta naught. And there's no horizontal acceleration, so that completes our x-coordinate as a function of time. For our y-coordinate, we start out at a height s above the ground. There's the change in the y-coordinate due to the initial velocity, which has component v naught sine theta naught, so that's plus v naught t sine theta naught. And there's also a vertical acceleration due to gravity, which gives us minus 1/2 g t squared.
Good. Okay.
Okay, so that's our kinematics of the apple and the bullet. Now, for there to be a hit at time t equals capital T, the coordinates of the apple and the bullet have to be the same at that collision time. So
Yes.
for a hit at t equals big T, we require that the x-coordinate of the bullet at time big T is the same as the x-coordinate of the apple, and likewise that the y-coordinate of the bullet is equal to the y-coordinate of the apple. Okay, so let's look at each of these in turn. For our x-coordinate, the x-coordinate of the bullet is v naught capital T times the cosine of theta naught, and that has to be equal to
D.
the x-coordinate of the apple, which is just d. So notice that I can solve this for the time of the collision, capital T, and that's just d minus v naught times the cosine of theta naught.
Okay.
Now for our y-coordinate, the y-coordinate of the bullet is s plus v naught capital T times the sine of theta naught minus 1/2 g t squared, and that's equal to the y-coordinate of the apple, which is h minus 1/2 gt squared. All right. Now Now, I can rearrange that. Notice that I have a minus 1 half dt squared on both sides, so those cancel out. I can rearrange that to write v naught times capital T times the sine of theta naught is equal to h minus s, so that the sine of theta naught is equal to h minus s over v naught capital T. But remember, we solved for capital T here, so I can substitute that in.
Yep.
So that gives me h minus s over v naught times 1 over t, which is v naught cosine theta naught over d. And so I can rewrite that as h minus s over d times the cosine of theta naught. So rewriting that, I have on the left-hand side sine of theta naught over cosine of theta naught is equal to h minus s over d.
So
and notice on the left-hand side, sine over cosine is just tangent, so this is just the tangent of theta naught. Now, think about what that means. If I draw a right triangle, where this is theta naught, and this is h minus s, and this is d. And so this is the same geometry we have here if we do the triangle like this. So theta naught is just the angle to the location of the apple just before it drops. So what this calculation tells us is that the correct thing to do if we want to hit the apple, if we know the apple is going to drop at the same instant that we fire, then we should aim at the location that the apple is at that instant. And we shouldn't try and lead the apple and fire below it or fire above it. We should aim directly at the apple. And what the kinematics tells us is that both the bullet and the apple fall vertically down at the same rate, and so that will give us a collision.
Yeah.
Now, it's worth thinking about two different cases, which I'm not going to solve for you here. The first is, what if the apple didn't drop? Suppose the apple just stayed in the tree, and I fired. If I aimed directly at the apple and the apple didn't drop, then I would miss the apple because the bullet would drop as it went across
Yep.
this distance d. Now, of
We
course,
will need
if the
to-
apple were big enough, or if the bullet were flying fast enough, if v naught was fast enough, then it might be that the amount that the bullet dropped wouldn't be bigger than the thickness of the apple, so I might still raise the apple. But I wouldn't hit the apple dead center. So if I knew that the apple wasn't going to drop, and I wanted to hit it dead center, I would have to choose some different angle, theta naught. We can sort of see intuitively that that angle would have to be a little bit steeper, so that the bullet would drop and then hit the apple. And so the way we would solve that is in our original kinematic equations. For the motion of the apple, x would still be a constant d, but if the apple wasn't dropping, then y of the apple would also be a constant. We wouldn't have the second term. We would just have
Yeah.
y equals h. And then I would have to solve for
Yeah,
a collision.
that's-
The other case to think about, that I'd like you to think about, is what if the apple begins dropping for a short interval before we fire? So that at the time that we fire our projectile, the apple is already dropping. Well, that's equivalent to saying that at time equals 0 when I fire, that the apple has some initial velocity, whatever velocity it's picked up by dropping in whatever interval it was dropping before. So now, my kinematics for my apple in the vertical direction, I would have an additional term here, a minus v naught t, where v naught is that initial velocity. And that's a different v naught, I should use a different symbol. It's a different v naught from the v naught of the bullet. But there would be an initial velocity, falling velocity of the apple that I would have to consider. So the particular details of what's happening with the apple change the kinematics, and it's worth thinking about how that would change your answer.
Okay.
We all regularly drive with a car. We want to get from point A to point B. Usually we like to drive with a constant speed. But what happens if there's a traffic light? Well, we have to stop eventually, which means we have to brake, and that makes the car decelerate. So there are different parts of motion when we ride a car. It can be constant, it can be accelerating, it can be decelerating. So let's consider this in a little graphic. We have a little car here, and it drives with constant speed until someone slams into the brakes, and the car will eventually stop. Let's add a timeline to this. Here we're going to put t equals 0. The point in time where the car stops, driving with a constant speed, is t1, and the point where the car has come to a complete stop is t2. And the problem now asks for what is the position function? What is the distance at any kind of time here as the car goes through these two different phases of motion? So ultimately we want to get to x of t. But we can't actually just write this up. We need to first look at other information that we have about this kind of setup. And what we have is information on the acceleration.
First
And we have to consider
acceleration
the
is
two phases
0.
separately. So we have here phase 1 and phase 2.
Acceleration is 0.
Phase 1 is from
And
0 to t1. And phase 2 is from t1
just
to t2.
v1.
And we know when a car is going with a constant velocity, its acceleration is going to be 0. So that keeps life easy for phase 1.
Yes.
And then when it brakes, well, we know it decelerates, so we're definitely going to have a minus sign. And it brakes between t and t1. And we need to multiply this factor here with a constant.
Yes.
So this is our acceleration information that the problem has given us. And we know, of course, that if we integrate the acceleration, we're going to get to the velocity function. And if we integrate that one again, we're going to get to our position function. So let's do that first for phase 1. And what is also important here is that we need to carefully consider the initial conditions. Again, what additional information is this problem giving us? So initial conditions, they always make life a lot easier. So it's important to carefully look for them. And what that means is we want to know what the distance is at t equals 0 and what the velocity at time 0 is. And we know the distance here is 0.
0.
And we know that the problem starts when the car is already driving with a constant speed. So that's going to be v naught.
v0.
So let's then make use of this and start integrating our acceleration. We want to get to the velocity. So v of t minus v of t equals 0 is going to be that integral. And here already we know that v of t equals 0 is v naught. So this already looks pretty nice. And now we have our integral here of a. And of course now t is an integration variable, so we have to give this a prime. And we're integrating from t prime equals 0 to t prime equals t. And when we plug this in, well, a is 0 in phase 1, which means actually our integral is going to be 0. That's handy. And from that, we will find that v of t equals simply v naught. All good. Now we need to integrate this to get to our position function. Same thing again, x of t minus x of t equals 0. Let's quickly check here what we know about x of t0. Well, it's 0 from the initial conditions. And now we have to integrate our velocity function here, v naught dt, again prime, t prime equals 0, t prime equals t. These are our boundaries. And this is simply going to be v naught t prime evaluated from 0 to t.
To t.
And we can add that. We can add that in there, and it's just going to be vt.
And
So
for
x of
second
t,
phase,
I can just write it here again. X of t equals v naught t. Okay, good. So half of the question half of the problem is solved. Let's look at the same things for phase 2. So let's consider the initial conditions for phase 2 now. And again, now we want to, in an analogous way, look at
now
the distance
x
of what we
is
know about the
equal
distance at
to
t,
v
1,
null t.
and the velocity at t1. And about the position, we know from over there that this is v naught
V
t.
naught t,
So our previous
yeah.
result now actually becomes the initial condition for the next step, right? Because whatever happens here sets whatever happens afterwards. So that's
And
nice.
vt1
And,
is
we know that
a
up to this moment here, this car
is
goes with the velocity of v naught.
v naught.
Let's consider a kinematics problem, and in this problem we want to focus on special conditions, how to think about that. So what I'm going to consider is some charged plates, and I have a charged particle, and it enters into this region of charged plates. And in this problem, there's two types of forces that are going to act on this particle. There's a gravitational force down, and we're going to talk about some constant force upwards whose magnitude is changing in time.
BT.
And what I'd like to do is know how strong does this force have to be, this B is a constant, in order for the particle to not hit the bottom. Now let's think about a little, when we get started on a problem like this, there's a number of different issues that we have to think about. The first issue is that how do we even sketch what we think will happen here? Well, a particle enters at time t equals 0. So this force is initially 0 when the particle enters. So the particle is experiencing gravitational force, and we should expect it to start to accelerate downwards. But then this force is increasing in time, and so at a certain point, these two forces will balance, and the particle will have no net force up, and gradually this force will increase, so the particle will experience a force up. So we would expect some type of motion where the particle starts to go down, but now it's starting to feel that force upwards, and it starts to maybe move upwards like that. So what I've done here is I've sketched a trajectory of motion to help me think about the problem. You're standing at a traffic intersection, and you start to accelerate when the light turns green. Suppose that your acceleration as a function of time is a constant for some time interval, t less than t1, and after that it's 0 for time after t1 less than some time t2. At the exact same instant the light turns green, a bicyclist is coming through the intersection, and the bicyclist has some initial speed and is braking with an acceleration of minus v2 for the entire time interval t2. And at time t2, the bicyclist comes to rest exactly where you are located. And we also know some initial conditions. So our initial conditions in this problem are that you're accelerating v1 at a rate 2 meters per second squared, and you do this for time t1 equals 1 second. And the bicyclist comes into the intersection, we'll call that v2 naught, that's the initial speed of the bicyclist, at 3 meters per second. And the question is, what is the rate of deceleration of the bicyclist, v2? Now, this can be quite a complicated problem, so the first thing we want to do is just make a sketch and think about what's involved. This problem involves two objects, you and the bicyclist. The person, that's you, has 2 stages of motion, and the bicyclist only has 1 stage of motion. So to get started, it always helps to choose a coordinate system and to make some sketches of the problem. So let's say we choose it's all one-dimensional motion, 2 objects, one-dimensional motion. And so we'll pick an origin at the light, at the one side of the intersection, and we have 2 objects, which we'll talk about, you, x1, and the bicyclist, x2. Actually, we don't know yet who's in front of the other. The bicyclist will be first in front of you. So now, how do we sketch the motion of these 2 stages of motion? So let's make a sketch. And let's start with the person. Well, the person, if we plotted their position as a function of time, this would be position in general, I'll just draw the person function, they're accelerating to a time t1, and then they're moving at a constant speed at time t2. Now, the bicyclist is a little more complicated, because initially, the bicyclist has this is at time t, person 1. Initially, the bicyclist has a non-zero slope, and they're decelerating, and they reach you with a 0 slope. So this graph, this is the x2, that is the bicyclist, and right here we have person x1. So now, to build a strategy, we can even look at our graph and see that from our initial conditions, we have some special conditions so from our strategy, will be to 1, figure out what this time is, and we know that the bicyclist at time t2 has come to a stop. So that's one condition. And we also know that the bicyclist comes to a stop exactly at the same position as the person, x1 of t2 equals x2 of t2. So those are 2 conditions that we can deduce from all of this given information. And now we can apply our kinematic relationships for both the bicyclist and the person and try to see if these conditions will enable us to deduce what v2 is. So let's begin with the bicyclist. So the velocity of the bicyclist as a function of time is simply the integration of that bicyclist, dt prime, from 0 to t2. This is 1 stage of motion. The acceleration is minus v2, so this is a very straightforward integral. This is just v of 2 t2. v2, this is minus the initial speed equals that, v of t2 minus v of the initial speed is that. And because we want this to be 0, we have a condition that t2 equals v2 naught divided by v2. So that's our first condition for the bicyclist. Now, we have to separately solve for the bicyclist position. That's easy. x2 of t is the integral of v2 t prime dt prime from 0 to t2, and that's just minus 1/2. We want to make sure that we get the displacement, but at x2 naught is 0, so we have x2 at t2 equals the integral of the velocity function, which is v2 naught minus v2 of t prime dt prime from 0 to t2, and so we get v2 naught t2 minus 1 half v2 t2 squared. And when we put this condition in for t2, this becomes very simply, it becomes v2 naught squared over 2v2. Substituting t2 into each of these expressions gives us that relationship. So that's the position of the cyclist at time t2. Now this is a little bit tricky to get the position of the person. So in order to do that, we first find the velocity of the person function.
Yeah.
It's a two-stage motion. So for the first stage of motion, the velocity of person 1, minus their initial velocity, which is 0, minus 1, 0, that's 0, equals the integral of b1 dt prime from 0 to t1, which is just b1 t1. And this velocity remains constant throughout the next interval. So we can write the velocity function in the following way: v1t equals b1t for 0 less than t1, and afterwards a constant velocity. Now, this is the function that we need to integrate to get the displacement. So let's get ourselves a little room here and integrate that. And we have x of t is two intervals. First, from 0 to t1, the velocity function during that time interval. And then for the second time interval, d to t2, the velocity function is constant. This is b1 t1 dt prime. Notice this is not a variable, but it is the time at the end of the interval. And when we make these two intervals, we get 1 half b1 t1 squared. Let's make this velocity at time t. So that's time t. This first interval goes from 0 to t1. And the second interval, we're going to make this the position at time t2. And we get plus b1 times t1 times t2 minus t1. We have a common term, t1 squared, b1 half b1 t1 squared, b1 minus b1 t1 squared. So this reduces to 1 half b1 t1 squared plus b1 t1 t2. And that's how we find the position of the person for our interval. Let's just review that to make sure, because we had to get the velocity function first, and then we integrated the velocity in each time interval correctly in order to get the position function. Now we can apply our conditions. Notice we already know t2 here, and we can now apply the second condition, which says that the position of the bicyclist at time t2, which we found to be v naught squared over 2b2, is equal to the position of the cyclist, of the person at that same time, so that's minus 1 half b1 t1 squared plus b1 t1. Now let's make that substitution for time t2, so that's v2 naught over b2. And now our problem is to solve for this time b2. And we're given b1, we're given t1, we're given v2 naught, and the only variable here is b2. It's a little bit of algebra to rearrange terms. What I'll do is I'll bring this term over here. So now we just do a little bit of algebra. We have a b2 I pull out. I have a minus b1 t1 b2 naught, and that's equal to minus 1 half b1 t1 squared. And now I can solve for b2. And so I get b2 is equal to vt naught squared minus b1 t1 b2 naught over minus 1 half b1 t1 squared.
Okay.
Now let's just do a quick dimensional check. B times t has the dimensions of velocity, so this is velocity squared, that's okay upstairs. B times t squared is dimensions of position, so what we have is meters squared per second squared divided by meters. That gives us meters per second squared, so we're pretty confident that we at least didn't make an algebraic mistake. And now our last step is to substitute in the numbers, and what we get is, if we put in the 3 meters a second squared, minus b1 times t1 times 3, so we get upstairs is minus 3 halves, and downstairs is 2 times 1 second, 2's cancel, so we get for b2, 3 halves meters per second squared when we put in the numbers. If we want to check our result, we can then see what time we get. T2 is 3 meters per second divided by our B2, which is 3 halves meters per second squared, so that's 2 seconds. And now the last check would be to see that the position functions correspond to that. Let's see if we can just do that quickly in our heads. Our position function for the person is v naught squared over 2b2, so that's 9 meters per second, 9 meters squared second squared over 2 times 3 halves meters second squared, and that comes out to x2 of t. This is a check, is 3 meters. And the x1 of t, we left out the 1 there, we should have had it. It's a little more complicated to put in here, but we'll just run the numbers quickly through. 2 times 1 seconds minus, that's a minus 1. 2 times 1 times 2, it's 2 times 2. So this is also 3 meters, and we actually have the right answer here.
Yeah, okay.
Last week, we discussed the kinematics of motion, how one describes the motion of an object by specifying its position, velocity, and acceleration as a function of time. This week, we will continue by discussing the dynamics of motion, how the application of forces on an object changes the geometry or trajectory of its motion. We will see that the applied forces and the change in trajectory are related through Newton's laws of motion. We will begin by reviewing Newton's 3 laws of motion. These were a landmark achievement in scientific thought. Most people who haven't studied physics tend to intuitively think in terms of the ancient mechanics of Aristotle, in which an applied force is required to maintain a body in uniform motion. Superficially, this seems to agree with our everyday experience, but only because friction plays such an important role in our everyday life. One of Newton's great insights was that applied forces cause changes in an object's motion, rather than being necessary to maintain uniform motion. Newton's laws were the end result of a great deal of careful definition, observation, and reasoning by many scientists up to and including Newton. It is a fascinating and compelling chapter in the history of science, but we will not discuss that history in this course. Instead, we will simply state Newton's 3 laws of motion as assumed postulates or axioms, and discuss their meaning and application. Finally, we will consider several specific examples of physical forces, such as gravity, contact forces exerted by a solid surface, like the so-called normal force, which acts perpendicular or normal to the surface, and friction, which acts parallel to the surface, pulling forces like tension in a rope or chain, and force exerted by a stretched or compressed spring, described by Hooke's law. Taken as a whole, this week will show us how to connect the two sides of Newton's second law of motion, F equals ma, the dynamics or application of forces on the left-hand side, and its relation to the kinematics, the change in geometry of the object's motion or trajectory, on the right-hand side.
Let me see. Good.
Newton's first law tells us about the motion of isolated bodies. By an isolated body, we mean one on which the net force is zero, one that's isolated from all interactions to as great a degree as possible. Newton's first law states that an isolated body moves in a straight line at constant velocity and will continue to do so as long as it remains undisturbed. Note that constant velocity might be zero. So, for example, an isolated body at rest will remain at rest if left undisturbed. An isolated body moving at constant velocity will continue to move at constant velocity as long as it remains undisturbed. It turns out that it's always possible to define a coordinate system in which an isolated body moves at constant velocity, perhaps zero. Such a coordinate system is called an inertial coordinate system. So another way of stating Newton's first law is that inertial coordinate systems exist. Now, it's worth pointing out that not all useful coordinate systems are inertial. The ones that aren't, we call non-inertial coordinate systems. As an example, imagine that I'm standing in an elevator that's accelerating upward. If we define a coordinate system that moves with the elevator, that coordinate system is accelerated with respect to an observer who is at rest. In that accelerated coordinate system, an isolated body would not move at constant velocity. So there are applications where using non-inertial coordinate systems is convenient. However, in this course, we will concentrate on inertial coordinate systems in which isolated bodies move at constant velocity. What if the body is not isolated? If a force acts on a body, then it will accelerate in proportion to that force. In particular, for a point like constant mass, Newton's second law tells us that the vector force is equal to the mass times the vector acceleration. So in other words, the acceleration caused by force is proportional to that force, and the constant of proportionality is the mass. And there are two important points I want to make about Newton's second law. The first is that forces always involve real physical interaction. Something must be acting on the object. If nothing is acting on the object, if the object is isolated, then we know from Newton's first law that an isolated body never accelerates in an inertial frame, it moves at constant velocity. So the only way to have an object move with a velocity that's changing, that is to have an acceleration, is to have a force acting on it. And Newton's second law tells us exactly how that works. The second point I want to make is that this statement of Newton's second law, F equals ma, is actually a special case. It's for the special case of a constant point-like mass. More generally, Newton's second law is written as the force is equal to the time derivative of the momentum, p. Now, we'll talk about momentum later in this course in more detail, but I'll just tell you that the momentum for a point-like mass is defined as the mass times the velocity. Now, for a point mass that's constant, these two equations are exactly identical. If you take the derivative of m times v, where m is a constant,
if
you just
m
get m
changes,
times vector a, and you get the first equation. So it's just a
different.
fancier way of writing the same thing. It doesn't convey any new information. So why do we talk about this as being a more general form? It's because this second form of Newton's second law can be generalized to a system of particles or a system where mass is flowing and the mass of something is changing. You can't describe that with F equals ma, but it's always true that for a given system, F equals dp dt. And we'll see how that works in more complicated mass flow problems later in the course. Newton's third law states that forces always come in equal and opposite pairs. What we can write that is if you imagine two objects, object 1 and object 2, the force exerted by object 1 on object 2 is equal and opposite to the force exerted by object 2 on object 1. This makes explicit that real forces always arise from a physical interaction. For any force in a problem, you should always be able to identify the other member of the interaction pair. Newton's third law is the most subtle and sometimes the most confusing of his three laws of motion, so I'd like to do an example that will help clarify how to think about it. So I'm going to take a very extreme example. Let's imagine the collision between a marble moving this way and a train moving that way. And so we'll say that the mass of the train, I'll write that as m sub train, and the mass of the marble is m sub marble, and obviously the mass of the train is much larger. I'm going to write that as several greater than sign, much larger than the mass of the marble. Okay? And so the question I want to consider is, at the instant that these two objects collide, which experiences the greater force? So think about that yourself for a moment. In terms of outcome, clearly the marble will be smashed by the train, whereas the train will not be noticeably affected by the marble. So your intuition might therefore suggest that it's the marble that feels the greater force. But that's incorrect, because Newton's third law tells us that forces come in equal and opposite pairs. And what that tells us is that each object will exert an equal but oppositely directed force on the other. Now, I chose a very extreme example to capture your attention, but that might seem like a surprising result, but Newton's third law tells us that the forces on each object are going to be equal and opposite. But just because the forces are equal doesn't mean that the motion will be equal. The accelerations of the two objects are vastly different because of their different masses. And the accelerations and the forces are related by Newton's second law, F equals ma. So if I write that in terms of the acceleration of the marble, a marble, is equal to the force divided by the mass of the marble, whereas the acceleration of the train is equal to, since I wrote F for the force acting on the marble, I'm going to write minus F for the force acting on the train. So that's minus F divided by the mass of the train. And so if I want to look at the ratio, how big is the acceleration of the marble divided by the acceleration of the train, and let's take the absolute values, we're going to talk about magnitudes here, that's going to be equal to the mass of the train divided by the mass of the marble. But the mass of the train is much larger than the mass of the marble, so the right-hand side here is a very big number. And that tells us that relative to the acceleration of the train, the acceleration of the marble is going to be enormous, even though the force experienced by each object is identical. Because of their different masses, their accelerations will be very different. So that gives us an example of what we mean by Newton's third law in terms of the interaction pair and equal and opposite forces acting. I want to reiterate that for any force in a problem, you should always be able to identify the other member of the interaction pair. So forces always come in pairs. It's important to keep in mind that these force pairs don't both act on the same object. They never act on the same object. The interaction pair always involves a pair of objects, two different objects. And let me just make that explicit with an example. The example I'll consider is, imagine a person standing on the ground. What are the forces acting on this person? I'll draw a force diagram here. Say,
the force of gravity.
Gravity, mg, acting downwards, and there's a normal force upward exerted by the ground. And those two balance to give a net force of 0, which is why the person is standing on the ground and not sinking down into the ground, for example. Now, you might look at gravity and the normal force and wonder if those are an interaction pair, and they're not, because notice that these two forces are both acting on the same object, the person. The interaction pair always comes from realizing what is exerting the force on the object. So let's look at each of these in turn. Gravity is exerted by the Earth. So if the Earth, and this means really the entire Earth, exerts a force mg on the person, Newton's third law tells us that the person exerts a gravitational force on the entire Earth of mg upwards. Now that might seem remarkable to you if you're just standing around on the floor, that you are exerting a gravitational force on the planet, but you are. However, this is like the example we just talked about a moment ago. The masses are extremely different even though the forces are the same. So the acceleration of the Earth due to this person's mass is negligible because the Earth is so much more massive than the person. But Newton's third law tells us that there is a tiny acceleration on the Earth due to the person. That is the third law pair for gravity. Mg downward exerted by the Earth on the person is paired with mg upward on the Earth exerted by the person. Now for the normal force acting on the person, that force is exerted by the ground. So the ground exerts an upward force n on the person. Newton's third law tells us that that means that the person must exert a downward force n on the ground. That is the interaction pair for Newton's third law for the normal force.
Good.
We can consider a given coordinate system as a reference frame within which we can describe the kinematics of an object. By the kinematics, I mean the position, the velocity, and the acceleration as a function of time. Basically, a geometric description of the motion. Some aspects of these kinematics will look different in different reference frames, and I'd like to examine that now. First, I want to define what I mean by an inertial reference frame. An inertial reference frame is one in which an isolated body, one with no net force acting on it, moves at constant velocity, where that constant velocity might be zero. Another way of saying this is that an inertial reference frame is one in which Newton's laws of motion apply. Recall that Newton's first law of motion states that an isolated object with no forces acting on it moves at constant velocity. So let's begin by considering an observer in a particular reference frame. We'll call that reference frame S and denote it by coordinate axes x and y. And let's consider an object that in that reference frame is at a position vector small r. We can then consider a second reference frame, which I'll call the frame S prime, and I'll denote that with coordinate axes x prime and y prime. In my example here, I'm going to assume that the coordinate axes in frame S prime are parallel to, but displaced away from, the coordinate axes in frame S. More generally, we could have the S prime coordinate axes rotated with respect to the frame S axes. That's a complication I'm not going to add now, but conceptually it's not really different. For simplicity, we'll stick to parallel axes in this example. So imagine we have two observers, one in frame S at the origin and one at the origin of frame S prime, both looking at the same object. Observer S will measure a position vector little r. Observer S prime will measure a position vector little r prime. The two observers have a relative position vector, capital R, which is the position of S prime relative to the origin of frame S. So what we'd like to see is how are these different position vectors related? Well, from the geometry of the diagram, we can see that the position measured by observer S, which is just little r, is equal to the position of observer S prime relative to observer S, which is capital R, plus the position vector measured by the observer at S prime, which is little r prime. I can rewrite that if I'd like to write the position measured by the observer at S prime in terms of what's measured by the observer at S. I could just rearrange this and write that little r prime is equal to little r minus capital R. Now, let's add a further complication and assume that the observer S prime is not just at a different location from the observer of S, but is moving at constant velocity relative to frame S. So we'll assume that frame S prime is moving at constant velocity with respect to frame S at a constant velocity vector v. Okay, so v vector is a constant. And in that case, my offset of observer S prime relative to observer S, which is the vector capital R, is a function of time. So capital R is a function of time, and it's given by the offset at time 0, which I will call capital R naught, plus the elapsed motion due to the constant velocity, which is capital V times time. So since capital R is a function of time, that tells me that in this equation, little r prime, the position vector measured by the observer in frame S prime, is also going to be a function of time, even if even if little r is a constant. So notice what that means. If the object is at rest in frame S, the object will appear to be moving, its position vector will be time dependent in frame S prime, because capital R, the location of S prime relative to S, is changing. So this relation tells us how the position vectors in the two frames are related. What about the velocities? Well, to compute how the velocities are related, we can just take the time derivative of the relation of the position vectors. So in this particular case, we have that the time derivative of the S prime position, d little r prime dt, is equal to the time derivative of the position in frame S, which is d little r dt, minus the time derivative of the offset of S prime relative to S. So that's minus d capital R dt. And I can rewrite that in terms of symbols for the velocity. So I have here the velocity little v prime, which is the velocity measured by an observer in frame S prime, and that's equal to the velocity little v, which is the velocity measured by frame S, minus d capital R dt, which we see is just capital V vector, which is the velocity of S prime relative to S. So this is how the velocities are related. And again, notice that if the object is stationary in one frame, it will be, so if it's 0 in one frame, it will be non-zero in the other frame. So in general, you will measure different velocities in the different frames, even if one of those velocities is 0. Now, how are the accelerations related? Well, again, we can just take the time derivative of the velocities to figure out what the relationship of the accelerations is. So differentiating this equation, I have that d little v prime dt is equal to d little v dt minus d capital V dt. But here something interesting happens, because remember, we said the capital V is a constant vector. And remember, capital V is the velocity that frame S prime has relative to frame S. Okay? So since capital V is a constant, that means that this term goes to 0. And so we see that the acceleration in frame S prime is equal to the acceleration in frame A. So if I have two reference frames, one moving at a constant velocity relative to the other, in general, I will measure different positions and different velocities for an object, as measured by the two frames. However, the accelerations measured in both frames will be identical. Because the accelerations are identical, we'll see that Newton's laws will look identical in the two frames. And we can see that in the following way. In frame S, we have that the force is equal to the mass times the acceleration. In frame S prime, the force F prime is equal to the mass times A prime. But A prime is equal to A. as we calculated here. So we see that the forces in the two frames are identical, even though the positions and velocities in general will be different as measured in the two frames for the same object, but the accelerations will be identical, and so the forces will be identical. So if one of these reference frames is an inertial frame, one in which an isolated body moves at constant velocity, then any other frame moving at constant velocity with respect to the first frame will also be an inertial frame. What this means is that you're always free to transform from one inertial frame to another. And what that means is that you can always transform to another frame that is moving at constant velocity with respect to an original inertial frame.
Okay. Makes sense.
Now that we've seen how coordinates are related between two inertial frames, I want to consider a slightly more advanced example for a moment, which is suppose that capital V, the vector velocity of frame S prime relative to inertial frame S, is not a constant. So in this case, suppose that frame S prime has an acceleration capital A relative to S. We now say that S prime is a non-inertial frame because it is accelerated relative to frame S. Now we saw that in inertial frames, one always measures the same acceleration for the same object, even though you'll measure different velocities in different positions in general. That's not going to be true in a non-inertial frame. In a non-inertial frame, the acceleration A prime is equal to the acceleration of frame S minus capital A, the acceleration of frame S prime relative to S. Remember, capital A is 0 for S prime being an inertial frame when capital V is a constant. But if capital V is not a constant, then capital A is not 0. So you will measure different accelerations in these different frames. Now what that tells us is that Newton's laws are going to look a little different. And let's see how that works. So now the force measured in frame S prime, I'll call that F prime, we expect that from Newton's second law to be the mass times the acceleration A prime. But that is the mass times the acceleration measured in frame S minus m capital A, the acceleration of frame S prime relative to frame S. Now I can rewrite this as two terms. One I'll call F physical, which represents the physical forces acting on the object. And the second term I'm going to call F fictitious.
Fictitious, yeah,
For reasons that we'll see in a
forces.
moment. So what this means is the following, is that an observer in frame S prime, in order to explain the motion of the object using Newton's laws, will have to invoke not just the physical forces that are acting on the object, which might be due to gravity, or rope pulling, or an engine pushing, or a hand acting on something, but will also have to invoke an apparent force, which I'll call F fictitious, that acts on everything. And in this case, F fictitious is equal to minus m capital A. But that force will not be associated, will not be identifiable with any actual real physical interaction. It's an artifact of the choice of coordinate system. It's an artifact of the non-inertial coordinate system that frame S prime is in. Okay? For that reason, we call it a fictitious force, and it's to be distinguished from real physical forces of the types that we've been talking about up until now. So you may have seen earlier that for the motion of an object in a circle around some center point implies the presence of an inward acceleration toward the center of the circle. So as a consequence of that, a rotating reference frame, for example, a reference frame that rotates with the Earth's rotation, is accelerated relative to an inertial frame. This results in a fictitious force that has two terms, a centrifugal term and a Coriolis term. You may have come across this Coriolis force and centrifugal force before. These are examples of fictitious forces because they arise from the choice of coordinate system. They're an artificial force. They don't correspond to actual physical interactions, but are an artifact of the rotating non-inertial coordinate system. Now in this course, we will confine ourselves to inertial reference frames, and therefore we'll only be considering real physical forces and interactions. However, there are advanced applications where the use of a non-inertial frame has certain advantages, and you may encounter those as you go to more advanced courses.
The motion of objects in space is governed by the universal law of gravity. So let's consider how this works. We have two objects here, object 1 and 2, and that could be two planets or two asteroids or two white dwarfs, black holes, any kind of object you can imagine. And they are mutually attracted by each other due to gravitation. So we have a gravitational force, and we label this as F, and this is the force on object 1 due to the interaction between the bodies 1 and 2. And here we have a force that's a force on object 2 due to the interaction between objects 1 and 2. And the objects are separated by a distance r, 1, 2. Now we want to derive the universal law of gravitation. How we're going to go about that? Well, Newton figured out a while ago that it is proportional to the masses of objects 1 and 2. So this one has a mass m2 and this one has m1. And it is also proportional to the square of the distance between the two objects. Now we need to do one more consideration and then we can derive this. We need to actually, well, first we need to pick some kind of origin from where we are considering these two objects to be. And this object here goes from the origin to there, and we call this r1. And then we have here r2, which also means that the distance here between object 1 and 2 is r12. And actually we know from vector decomposition that r12 equals r2 minus r1. So just this minus this gives us this distance here. Now, if we want to write down the universal law of gravitation, we also, there's a magnitude component to it, and we also need a direction. And we haven't yet chosen a coordinate system. We could, of course, choose our usual way of placing the I-hat direction in the x-coordinate, the x direction, and the j-hat coordinate in the y direction. But when we deal with the universal law of gravitation, it's actually better to adopt a slightly different coordinate system. Everything in space usually orbits one another, so it's much better to think in a radial direction rather than just normal Cartesian coordinates. And so in this case, we're going to choose an r-hat vector, which gives us a radial direction, and we're going to do this here. So this is going to be our r-hat direction on object 2, and here we have an r-hat direction 1. And we're going to come back to the r-hat unit vectors later. For now, we can just write here quickly down the definition for a unit vector. So our r-hat 12 is, of course, the vector itself, r12, divided over the magnitude of the vector. We can write it like this. And now we can write down the gravitational law. So the force on object, we're going to look at object 2. The force on object 2, due to the interaction between objects 1 and 2, is proportional to the mass of the two objects. We already said that in the beginning, and the square of the distance between the two objects. But what about the direction? The direction here, we're looking at object 2, we placed r hat unit vector to point down, but the force is going in the opposite direction, so in the negative r12 hat direction. So we have to add a minus here and then r12 r hat. And as it is the case with most of these laws, there's a proportionality constant, and Newton called this capital G. And G, as we know today from experiment, is 6.67, 10 to the minus 11. And then in terms of units, we have Newton. Force goes in Newton. We have mass, this is kilogram squared. And we have meter squared. So that are the units, and if you plug those in, then the units of the whole equation will work out. So let's quickly consider the force in object 1 to see what's happening over there. So we have F21 equals minus G M1 M2 over R12 squared. And in terms of the unit vector, we now have R21 hat here going. So again, this minus goes with this unit vector, and that one is pointing here in the opposite direction than all force. So that's all good. But what we see from this one here, and actually from our diagram already, that R12 equals minus R21. And so we see from this then that actually Newton's third law, every action has an equal and opposite reaction, is true for this little setup here as well, because the forces are of opposite direction and of equal magnitude. The little prince lives on his asteroid B612, and he really likes to watch the stars. And what he really wishes for is to watch the stars while floating, to have the best possible view and to just immerse himself in the stars. And so the little prince has to think if there is a position in space with respect to other celestial bodies where the gravitational force will just cancel so that he can float. Let's look at that. So there's the planet of the businessman. We're going to give it the mass M1. And there's also the small planet from the lamplighter floating around with mass M2. And we know that gravitational forces act radially. If we put the asteroid B612 somewhere here, then maybe we find a constellation where gravitational forces cancel. So let's start by placing the little asteroid over here. And what is this body experiencing in terms of the gravitational forces? Well, it's going to experience the gravitational force of object 1. So we have object 1, or F1m, due to the interaction between object 1, so the businessman planet, and our little asteroid here. And then we also, of course, have the same direction here due to the interaction of object 2 and our little asteroid, so that would be F2m. And you can clearly see that if we tally out these forces, they're not going to add to 0. So this is not a good location for the little princess asteroid to be. The same would be true if we put it out here. It will experience those same forces again. What do we have here? 1m and 2m, just going in the opposite direction. But you have guessed it already, we can find a spot here in the middle where one force goes in this direction. So this is
Cancels the other.
F2m. And actually we should give those forces direction. And the other body exerts a force going in the other direction. And so we can see that we now just need to find that exact position here in between. They already on a label. And so let's place the asteroid place gravitation between m and then m1 on the distances m2. And now we have d minus x gives us this portion, d minus x squared, also in the I hat direction. And that needs to add up to 0, because that's what we want, right? We want this to, if it adds up to 0, then we have no gravitational forces acting on the asteroid. So now we need to solve this for x here. And then the first step, we see that actually g and m will fall out here. And then we're left with m1 over x squared minus plus m2 over d minus x squared. And we can write that as m2 x squared minus m1 d minus x squared. And what you see here is that this will turn into a quadratic equation. And if we do a few steps of arithmetic and then write down the general solution to this quadratic equation, we will find this here. X equals 2 dm1 plus minus 2 dm1 squared minus 4 m1 minus m2 m1d squared, and then the square root of that over m1 minus m2, and actually we need 2 of those. So we have this quadratic equation here, or the solution, and we now need to consider one more thing, namely this equation here is only valid if, where can I write this? Here. If x is between 0 and d, right? If I, in position C, my x is larger than d, which means this, this force here flips sign, and then this would be different. So this plus here refers to x being less than d. And we have to decide which of the two signs here gives us the correct, which fulfills this requirement here. So this simplifies to x equals d m1 plus minus m1 m2, and here we have a square root, and then here we have another bracket over m1 minus m2. And we need to get this term here smaller than 1, or to be smaller than 1, if the x is between 0 and d. And as it turns out, that is indeed true if we use the minus sign here. Let's consider the universal gravitational law a little bit more. Let's consider two objects in space. Let's say this is the sun, and we have the Earth here, or the Earth and the moon. and of course they're orbiting each other. So we can pick a coordinate system that goes radially, and so we're going to have an r hat direction here, and we're going to call this the r hat direction between objects 1 and 2. What force is acting on this little moon here? Well, it's the gravitational force going inward. It's the force F12 on object 2 due to the interaction between bodies 1 and 2. For that, we can write down universal gravitational law, F12 equals minus g, the gravitational constant, m1, m2 over r12 squared. That one is the distance between the two objects, times r12 hat, and the minus goes actually with the unit vector here because the force goes in the opposite direction from our r hat. Let's now consider, here's the Earth again, and we're going to move the moon, or a little moon rock, right to the surface of the Earth, and we want to now calculate and consider what kind of forces act on this moon rock, and what is the gravitational acceleration that this moon rock on the surface of the Earth is experiencing. So here we have the Earth. Earth has one Earth radius, and it has an Earth mass, and our moon rock has the mass m. And we know from this exercise here already that, of course, this gravitational force is acting on our moon rock as well. That hasn't changed. What we are now considering in addition is that this moon rock is also experiencing a gravitational acceleration due to this force, and it goes inward as well. So it is experiencing an mg. And we know that that is the same as the magnitude of this force here. So we can equate that with g, and then we have the Earth mass and the mass of the moon rock times the distance squared, so an Earth radius squared. And from that, we already see that A, we can cancel out the small m's of the moon rock, and we get to g here. So we can calculate the gravitational acceleration, which is capital G Earth mass over Earth radius squared. So if we have this kind of information, we can determine the gravitational acceleration, and of course it will change depending on which object we are considering. It would be different if we plug in the solar mass and the solar radius, or the moon mass and the moon radius if we consider an astronaut standing here on the moon surface. Now let's put some numbers into this equation. So we have G is capital G 1.7. This number can either be calculated if you know capital G, the gravitational constant, or you can determine the gravitational acceleration through an experiment, and together with the Earth mass and the Earth radius, you can actually calculate the gravitational constant there.
Correct. Contact
Let's consider what happens when we have an object that's moving on a horizontal surface. So here's our object, and here's our surface. Now we want to look at a special case where we're applying force F to the object, and the object is moving at a constant speed. Then what we see here is that there has to be some type of force that's opposing this object, the interaction between the object and the surface, that's distributed over the surface. For this, I'll write an arrow here to express that force. That's the tangential component of the force. The object is also pressing down on the surface is pressing up on the object, and so there's another perpendicular force to the surface, which is referred to as the normal force. And the total vector sum of these two forces, the perpendicular part, the normal force, and the tangential part, is referred to as the contact force. This is what we'll call kinetic friction. Now, when the object is moving at a constant speed, we know that from experiment that the kinetic friction, the magnitude, is proportional to the magnitude of the normal force, and the constant of proportionality is called the coefficient of kinetic friction. Now, this law is telling us something very interesting, that two key properties are, one, that it's independent of the contact area. Now, what do we mean by that? So let's look at the following picture. Suppose we have two objects of the same mass on the surface. We're applying force F, and the contact area here, A1, and we have a similar object, the same mass, on the same surface, and both objects are moving at a constant speed. Now, these objects have different areas of contact, A1 and A2, but the force necessary to move the object at the constant speed is the same. And because of that, the kinetic friction is the same, and that indicates that it's independent of the contact area. And the other key property here, which we'll write over here, is that it's independent of the speed of the object. So we'll write that as independent of the velocity. And these three properties of kinetic friction are crucial for understanding the motion of objects across the surface, but we still don't have a very good theoretical model for explaining this, although today there's a lot of contemporary research which has made a lot of progress in understanding this interaction. We consider the case where an object is moving along the surface, but now let's consider what happens that if we apply force F here, and the object stays at rest. Well, we still have the normal force distributed over the surface, but now because the object is at rest, there's another, the contact force now is what we call static friction, the tangential part of that. And the contact force is still the perpendicular part, the normal force, plus the tangential part, which we refer to as static friction. Now, what happens with static friction is that if we don't apply force at all, then there's no static friction. In fact, you can see in the simulation that if we slowly increase the applied force, then the static friction force gets bigger and bigger. It depends on what we're doing to the system. But at a certain point, when we apply a large enough external force, the object suddenly starts to slip. That's what we call the just slipping condition. And the reason for that is static friction has reached its maximum possible value. That has to do with the physics of the interaction between the surface and the object. So also there's a very subtle thing, is that as you see when we pull the force and it just slips, suddenly the friction has gone from static to kinetic friction, and it's gotten a little bit smaller. How do we express those properties? Well, what we have is the idea that the static friction can vary in magnitude between 0 and some type of maximum value, depending on the other constraints on the system. And the maximum value of static friction, we have a force law, which is that it's again proportional to the normal force, but the coefficient is called now the coefficient of static friction. And this coefficient of static friction is slightly bigger than the coefficient of kinetic friction, which explains why that arrow got a little bit smaller when it just started to slip. Now, again, like kinetic friction, static friction is opposing this external force. And depending on the direction that the object moves, for instance, if we applied the external force in the opposite direction, here, then the static friction that's distributed over the surface is opposing that force. But there may be many systems in which we're actually not quite sure which way static friction points. And as the course develops and we look at more complicated examples, we'll see that the direction of static friction can depend on all the other constraints on the system.
Here we have a little block that sits on that surface, and well, what can one do with the block? You can push it, or you can pull it, and that's exactly what we're going to look at now. So I can exert a pushing force onto this block here, F push, but I could also pull it, like this, F pull. And the question is, how can we formalize this a little bit more? We can now also look at a small piece of rope or string, and I could, in a tug of war, I'm going to pull here, and I'm also going to pull here, and we'll see who's going to win. So we have two pulling forces here on either side. In a slightly different scenario where we're going to put both of these things together, we have a block here sitting on a surface, and we have a little string attached to it. And let's say we have a pulley here, and the string goes around there, and there's a little mass hanging here. We want to now describe what this force is here that's pulling things, and for that we have to look at what's going on in that little string. So let's draw another string. And
I always hit a problem with this.
Take an imaginary cut right through the middle here, and I'm going to draw both pieces here. This is the left part, and here is the right part. And what's happening in this rope here now? Well, there is a force acting on the left object due to the interaction with the right one. And here we have a force on the right one due to the interaction with the left piece. And that, of course, happens anywhere. I take a cut here along the line, and we can even formalize it a little bit more by just placing our coordinate system here. Let's say x equals 0 here. And so for all x along this line, we always have these pairs of forces. So they are an interaction pair. And if I look at the rope from afar, they will cancel out. But if I look at what's going on inside the rope, then this is what they are. And we know from Newton's third law that FRL equals minus FLR. So they are forces of the same magnitude, but the opposite direction. If they weren't the same, then my rope would get in trouble. But what we want to define now actually is tension. The tension force that is that's happening along this rope here, tug of war if someone pulls from the outside. And for that, we're first going to look at the magnitude of our interaction pair here, FRL, and that of course equals the magnitude of FLR. And we're actually going to define now this magnitude here as the tension force. And that is true for all x along this line here, that we have this the magnitude, that this is the magnitude of this force here. And from now on, we're going to call, when we talk about tension in a rope, and we talk about the magnitude of one of these internal forces here.
Today we'd like to discuss tension in a rope. Under what conditions is the tension uniform? Recall that if we had a rope, and say we were pulling, here's our one end, we'll call that, we're pulling at this end with force A, and we pull on this end B with a force B, that what we meant by tension at any point in the rope was that we took an imaginary slice of the rope P, and we looked at the two sides, and here, if we call this the left side, and this the right side, then on the left side, we have that the right side of the rope is pulling the left side of the rope by some force F, and this is the left side, and the right side is being pulled by the left side, so that's the right side being pulled by the left side, and what we defined the tension at the point P was to be the magnitude of this action-reaction pair, and that's how we define tension at a point inside a rope. Now we'd like to address the question is, when is the tension, under what conditions can we say that the tension is uniform, which means that at all points P, the tension is the same. In order to analyze this, we'll apply Newton's second law. So let's begin with the same situation as before. Let's consider a rope where we're pulling this side with force at the end. By the way, we can call this the tension at that end, T of A, and on this side, we can refer to this as the tension on side B. Now, suppose that our mass of the rope is non-zero, and we now want to apply Newton's second law, but let's also apply the condition that the acceleration of the rope is non-zero. So you're holding the rope under some tension by pulling both sides, but the rope is not accelerating. And so what does that mean when we apply Newton's second law to the rope? Well, let's just arbitrarily call that our positive direction. We see by vector decomposition that we have TB minus TA equals mass of the rope, but because the acceleration of the rope is zero, this side is zero, and we can use Newton's second law to conclude that the tension in the rope is uniform when the rope is not accelerating. And this is what we'll call our case one, A0, tension in the rope is uniform. Now let's suppose, case two, that A is not zero, and so now we have the rope, this is point B, here's point A, we'll choose a uniform direction, A, and now we can see, when we apply F equals NA, that TB minus TA equals mass of the rope times the acceleration of the rope, so you're pulling such that TB is greater than TA by precisely the quantity mr times A. And so the tension at the ends are not the same, and therefore the tension in the rope is not uniform. Now there's a special case here that we want to consider. So even though A is non-zero, let's assume that the mass of the rope is very small. And this is often, people call this, assume the rope is massless. Well, that's a little strange. We can say the very, very light string is often the same type of modeling. And under those circumstances, with that assumption, you see that there is no contribution here. And with that assumption that the tension is approximately uniform, ropes are not massless, there's a small difference. But under those circumstances, when we say a very light rope, that even if it is accelerating, implies that T is uniform in the rope. And we can say the rope is under uniform tension. And we will often refer to this case when we analyze problems where we're pulling objects, for instance, in a typical pulley problem. One of our classic problems to analyze using Newton's second law is the motion of two blocks with a rope that's wrapped around the pulley. So imagine we have a pulley P, and we hang from that block 1, and we hang from that block 2. The pulley is suspended by another rope, and it's attached to a wall. And let's now try to use Newton's second law to analyze this motion. Now, going back to our methodology, the first thing we want to ask ourselves is to identify what are all the moving pieces. So I'm going to make my first assumption here that the rope pulling surface, so that's right here, is frictionless. Now, what that assumption means is that the pulley will remain at rest. And therefore, when we want to break this problem down, our first question is to identify all the moving objects. And so we really have three. We have mass, which we label by 1, 2, and the rope. So our goal now is to identify all the moving objects and to draw free body force diagrams for each moving object. Now, one of the things I'm especially interested in talking about is to keep in mind to identify action-reaction pairs. So as I go through and draw these free body diagrams, we want to ask ourselves, what forces form Newton's third law action-reaction pairs? So what I'll do is I'll start with object 1. Now, object 1 has a gravitational force, N1G, and the rope is pulling object 1 up with a tension at the end of the rope, T rope 1.
Okay.
So the action-reaction pair to N1G is the Earth, is the force of this mass on the Earth, which we're not considering. What about the rope? So now let's draw a picture of our rope. And mass, this object here is pulling the rope down. And so we have on the rope, object 1 pulling it down, and this is our action-reaction pair. What are the other forces on the rope? Well, over here, object 2, T2, is pulling the rope down with a tension at the end of that rope. Now also, the pulley is exerting a force on the rope upwards because we have that force. And so these are the force diagrams on the rope. Now, what about the action-reaction pair to T2 rope? Well, let's continue and draw 2. We have, again, gravitational force on 2. The Earth is the action-reaction pair. The force of 2 on the Earth upwards is equal to M2G of the Earth downwards. We're not drawing the Earth in this picture, so we don't show it. Now here is the force of the rope on 2, and there is our other action-reaction pair. So these are the Newton's third law pairs in this object. Now that we've identified all the forces, we want to apply Newton's second law to each of these objects that are moving. So let's begin by remembering that if our next assumption here is assume that the mass of the rope is very light, and then the tension in the rope is constant, and the implication of that is T2R equals T1R. And that's why we can now identify this as T and that as T.
Yes.
A little bit later on, when we talk about pulleys that have mass with friction between them, the tension on the two sides of the pulley will not be the same. But for the moment, we've made these assumptions, and that holds. And now we just really have objects 1 and object 2 to analyze. And so one of the things that helps a lot is we need to choose unit vectors in order to write down the vector equations for Newton's second law. So let's just here assume for ourselves that n1 is greater than n2. This gives us some feeling for how the system moves. I like to do this because it gives me a way to choose my unit vectors to make all the accelerations positive. So when n1 is bigger than n2, I expect n1 to go down and 2 to go up. And that's how I'm going to choose unit vectors j hat 1. Now here's the very interesting thing. We choose a separate coordinate system for each object. So I'm going to write that down. We want to choose separate unit vectors for each object. And our accelerations will be with respect to those unit vectors. This is where a lot of people get tripped up. So here, I'm choosing j hat 2. And when I choose that, I expect a2 to be positive because 2 is going up in the direction of j hat. And here, I expect a1 to be positive also because 1 is going down. Now I can draw Newton's second law on 1. So I have F1 equals M1A1. And now I analyze my forces. N1G is in the positive j hat direction. T is in the negative j hat direction. So I have N1G minus T equals N1A1, which I'm expecting to be positive. And in the same way, on 2, F2 equals M2A2. I look at my force diagram. Now notice, j hat is up, so T is positive. M2G is minus my direction. M2G equals M2A2. So I now have two equations. But when I look at these equations, I see that I have three unknowns. I have T, A1, and A2. But I have a constraint. Because these objects are moving together, and the way I've chosen the coordinate systems, A1 is equal to plus A2. Both are positive with respect to my choice of coordinate systems. And so these two A's are the same. And now I can solve my equations for T and A. And let's quickly do that. N1G minus T equals N1A. And over here, let's solve for the tension for the accelerations here. T is equal to N2A plus N2G. And when I substitute the T into that equation, we'll find some space for that. We'll write that as, if I put in the N2 minus N2A minus N2G and bring the N2A to the other side, then it's a little bit of algebra, but I think you'll trust me that this is N1 minus N2G over N1 plus N2. Now, we're almost done. We need to check our answers. First of all, does it have the dimensions of acceleration? Answer, yes. Mass divided by mass. G has the dimensions of acceleration. So that's my first check, always with my algebra. Second check, what if N1 is equal to N2? Then the acceleration is 0. I expect them to be balanced. I've said that N1 is greater than N2, positive sign. My A is positive. That's how I set my coordinate system, so I expect that too. By the way, our symbol A was equal to those. And so I'm pretty confident that my result is correct. And that's how we apply Newton's second law to the pulley with several assumptions: frictionless surface, massless rope, and think about how we chose our unit vectors. Each object gets its separate coordinate system. I'm not using the same coordinate system for each object. I could have, but then there would be a subtlety to this condition. The accelerations would be opposite in sign. We now would like to analyze the force law on an idealized spring, a force law called Hooke's law. Let's begin by drawing an ideal spring connected to an object on a frictionless surface. So we'll draw our object. We'll draw our idealized spring, this surface here is going to be frictionless. And this is a wall, and we draw it like that. And now what we'd like to do is to introduce the force law for spring, a force law which will be called Hooke's law. So the way we'd like to analyze this is by drawing two pictures. Our first picture will have the spring at an equilibrium picture. So let's draw the wall again, and let's draw the spring and our object. And this is called the equilibrium picture. So I'll write equilibrium picture. And now what we'd like to do is draw a picture, a dynamic picture at some arbitrary time t. So here we have a dynamic picture at time t, and I'll draw it in a second. So we draw the same object, and now we're going to move our object to some arbitrary position. In this case, the spring has been stretched. Wall, frictionless surface, and now I'm in position to choose a coordinate system. So what I'll do is I'll choose my origin at the edge right here. This is called x equals 0. I'll show it in the dynamic picture. And my coordinate function for the object here, I'm going to refer to that as x of t. Now notice that this coordinate function is also an indication of how much the spring has been displaced. As far as directions go, we'll have an axis, and this is our plus x direction, so usually we indicate that with a unit vector I. And now Hooke's law is the statement that the force on the spring, that the force on the object,
chi x.
F, is proportional to how much the object has displaced, which represents either the stretching or the compressing of the spring. So it's equal to minus kx I hat. Now what does this minus sign mean? Well, this is an example of what we call a restoring force. And let's look at a couple of examples. When x is positive, that means that the object has been pulled out from the equilibrium position. The spring is undergoing tension. It's being stretched apart. The molecules in the spring that constitute the spring are being pulled apart. And there's a restoring force inside the spring. This is an atomic force in nature that's pulling the spring backwards, hence exerting a restoring force on the object. So this force is in the minus I hat direction. It's restoring in that direction. I'll draw the force like that. Now suppose we drew another picture where the object is pushed in, compressing the spring. So let's draw once again the diagram, and let's show the spring under compression from our equilibrium position. Now here we have again that x of t, but in this case x of t is negative, and so this is extension, so we'll call that case A. In case B, when x is less than 0, it's under compression, and then we see that with x negative and the additional minus sign, the force is in the positive direction. And so in both instances, the force is a restoring force back to equilibrium. So the restoring force, whether you're under extension or compression, is always pointing, let's call it, is the direction of the force is towards the equilibrium position. And this example of a restoring force is also only proportional to x. And so in that case, we can add the word linear, because it's just to the single power x. And this is an example of a linear restoring force, and this is a model for an ideal spring. Now, this constant k is called the spring constant. And the units of the spring constant, if you divide the units of force by the units of distance, so we have SI units, are Newton over meters, and that's the measure of the spring constant.
Yeah.
So I would like to tell you about friction today. Friction is a very mysterious subject because it has such simple rules at the macroscopic scale, and yet, as I will show you and tell you a little bit about today, very different rules at the nanoscopic scale. So I would like to tell you about friction at friction at the nanoscale. So at the macro scale, there are classic rules that were discovered very early on for macroscopic objects. It was actually Leonardo da Vinci who found the first laws of so-called dry friction. So this was da Vinci as early as in the 15th century. And basically he discovered that friction depends on the force, on the weight of the object on the surface, and that there's a certain coefficient depends on the material. It turned out that da Vinci did not publish his notes. They were just hidden in his notebooks for a long time. And so until in the 17th century, we discovered the very same laws that da Vinci had found. And these are two very simple laws. One is, the first law is that if you have an object sliding on a surface, so there's a force that you're pulling on the object, and there's a friction force acting in the opposite direction, then Amantour found that the friction force is proportional to the normal force. So the normal force is the weight of the object. So he found that the friction force as a function of normal force is just a simple linear dependence. So if you make the object twice as heavy, the friction force will be twice as large. This makes maybe sense. It agrees with our intuition that maybe an object twice as heavy should have a force twice as large. The second law of friction is much more surprising. Namely, that if you have two objects of the same weight, so you have the same normal force, but of very different areas of contact, then the friction force is the same. So if you have a friction force for this object, let me call it friction force 1, and the friction force of this object, friction force 2, then the friction forces are the same. 1 equals friction force 2. So surprisingly, the friction force is independent of contact area. Friction. This seems very counterintuitive because if you think of friction as some kind of sticking, some kind of effect where two surfaces rub together, then we might naively assume that the larger the surface, the larger the friction force. One maybe intuition why this might not be the case, or one possible explanation is that surfaces always have roughness, and so the actual contact area between two surfaces, so if I really draw the surface of the object here, then the actual contact area between two surfaces might not be the observed area of the macroscopic object. And so this is maybe one way to explain why the friction is independent of the area, because it might only be proportional to the actual contact area of the system. We've already described two of the laws of macroscopic friction. There's a third law that was actually discovered by Coulomb,
And again, this is a little bit surprising result, namely that for this type of friction, the drive friction, it is independent of the velocity of the object. So this is, for instance, something that is not true for air resistance. If you drive a car, the faster you go, the more friction there is, the more air resistant there is. But if you have two surfaces sliding on top of each other, then Coulomb found that the friction force is independent of velocity. Again, this is something quite not quite, but somewhat counterintuitive, and as I will show you a little bit later, it actually is no longer true when you look at the nanoscale. Coulomb was also the first one to distinguish static friction, which is the force with which an object resists motion for a while. You make the force larger and larger, so for a while the object will stick, and then it will start sliding. So he distinguished static friction from dynamic friction. And because we have this law that says that the friction force is proportional to the normal force, I will remind you of the first law, the friction force being proportional to the normal force, like so, we can define a slope. So we can write the friction force as some slope mu times the normal force. These are both forces there, so they have the same units, which means that the so-called coefficient of friction, which could be either for static friction or for dynamic friction, for kinetic friction, this coefficient is just a number. And typically, this number is between 0.3 and 0.6. This makes a lot of sense. The friction force is not quite as strong as the normal force, so the friction force of which an object resists motion is not quite as large as the normal force of which it pushes down on a certain surface. However, surprisingly, there are materials where mu is actually larger than 1 is possible. So for instance, for rubber. Which means that an object can be harder to pull sideways than actually be pulled to, it can be harder to pull an object sideways than to actually lift it from the surface. So this is a surprising result. Now it turns out that despite these very simple laws, our fundamental understanding of friction is rather limited. So for instance, nobody in the world can predict this coefficient mu of friction. Nobody in the world can, from microscopic or principle, say, being told what the two surfaces are, say, plastic or wood, what is the friction coefficient, can you calculate it for me? We cannot predict it, we can only measure it and then tabulate it, make a table and say this kind of object or this kind of surface has this kind of coefficient for friction. So that's one, if you want, failure of physics. How is it possible that we can't describe and quantitatively describe something as simple as that? Also, in many instances, we would like to change the coefficient of friction. Typically, we would like to reduce friction because friction is something where we dissipate energy. It is estimated that as much as 3% of the nation's GDP is wasted, in quotation marks, on friction. So friction destroys energy in the amount of billions and billions of dollars. Cars driving on streets, machines working, and so on. Sometimes friction is, of course, desirable. If you want to stop your car on the road, you want friction to actually work. You wouldn't like to do away with it completely. But in many instances, it's just a source of energy loss. So if you could even make a small change in friction, this would be not only important for science, but it might also be very important for technology. So here I've told you about friction of macroscopic objects. Now people, chemists, physicists, other scientists, engineers are able to build smaller and smaller machines. And there's tremendous interest to build nanoscopic machines that are maybe only a few molecules or a small number of molecules or atoms wide and big. And there's been tremendous success. People have built nanopumps, tiny pumps, even a tiny car consisting of a relatively small number of molecules that can move on the surface if you inject with electrons. So as I would like to tell you about is that how bad friction is at the nanoscale. So let's ask the following question. How bad is friction at the nanoscale? Your general intuition might be that friction gets worse at the nanoscale simply because the bulk, the size, the volume of an object is what determines how many atoms are in it, whereas friction is a surface effect. And because the volume increases more quickly with the size of the object than does the surface, you might think that, yeah, probably there's a bigger problem with friction at the nanoscale than there is for macroscopic objects. To illustrate how bad this really is, let's consider a tire of a car. So this tire is rolling as your car is driving, and we can try to estimate what happens to the wear of this tire. So let's say that this tire maybe wears off. Wear is of the order of maybe, let's say, 10 millimeters every maybe 50,000 kilometers. So that means we take off a number of atomic layers here every 50,000 kilometers. Now, how many atomic layers is 10 millimeter? If we say that one atomic layer is on the order of, let's call it 1 angstrom, which is 10 to the minus 10 meters, then 10 millimeters is 10 to the minus 2 meters. So that is equal, since one layer is 10 to the minus 10 meters, that is equal to 10 to the 8 atomic layers. We can also ask ourselves, how far has this, how far has the tire been moving? So if we assume that the circumference of the tire, so this is the radius of the tire, let's guess that maybe the circumference of the tire here, which is given by 2 pi, is on the order of 1 meter. Then this means that 50,000 kilometers, or 5 times 10 to the 7 meters, which is 50,000 kilometers, is basically 5 times 10 to the 7 revolutions. So in 50 million revolutions, 5 times 10 to the 7 revolutions, we lose 10 to the 8 atomic layers. So it comes out that we lose 1 to 2 atomic layers per revolution. If we had used maybe the size of an atom more closely as 2 angstroms, we would come out at about 1 atomic layer. So this is a remarkable effect. Even when we drive our car, on each time the tire rolls around, we leave 1 atomic layer on the street. For macroscopic objects, as you see, it doesn't matter. We can drive a very large macroscopic distance before we wear off a few millimeters of the tire. But if the tire of the car was itself only a few atomic layers big, then you see we would have a huge problem. So this is why people are interested in understanding and maybe manipulating friction at the nanoscale. So what does friction at the nanoscale really look like, and why are people interested in it after so many centuries of first time studying friction? One reason is that now one can do experiments at the nanoscale. And the new tool that has enabled that is what is called an atomic force microscope. What is an atomic force microscope? Well, it's essentially a very, very sharp tip, atomically sharp tip. So you have a surface here, which consists of atoms, and these are individual atoms. trying to study the friction. And now what you do is you bring an object here, shaped in the form of the tip, which also consists of atoms. And the object is so sharp that you have ideally just one atom near the surface, one or more atoms near the surface. So this is what an atomic force microscope is. You can pull on this with some force, and then you can try to measure the force of resistance, the friction force that is due to the interaction between the atom near the surface and the atoms forming the surface. So we might call this the substrate, and this would be the moving object. And we can either study static friction by pulling the object but not with a force large enough to move, or maybe we can have the object apply larger force to the object starts moving at a certain velocity v, and we can measure friction. Now this, as simple as it may seem, is still too complicated for physicists. So we try to make the model even simpler. So how do physicists do this? Well, they say that the surface still consists of atoms, but now we're most interested in what happens to this tip. We're going to say, well, somehow what matters is that this atom is bound to the tip. So maybe we can model it in the following way. We have here the macroscopic part of the tip, and then we're going to say that the surface atom is really bound in some way to the tip. And the simplest way that we can imagine the surface atom to be bound to the tip is via some spring, with some specific spring constant. So basically, the one atom that makes the contact with the surface is bound via spring to the rest of the tip that is moving, to the rest of the moving object. So this is how we view the tip as physicists to make a model. And then how do we view the surface to make a model? Well, we say this is really a periodic arrangement of the atoms. So maybe it makes sense to kind of assume that the associated potential is also periodic at the atomic scale. So this is the potential as a function of position. So basically, we model friction as spring plus periodic potential. This is a very simple model, and it was first introduced now about 90 years ago, so by Prandtl, by a German physicist called Prandtl, and by another physicist called Tomlinson, and this is called the Prandtl-Tomlinson model. And they discovered it, or introduced it in 1928 and 1929. And it turns out that this very simple model of a spring and the periodic potential captures much of the essence of non-friction. So as physicists, now we have a spring and the periodic potential. How do we think about this? Well, one way is to think about the energy in the system. So we can plot the energy as a function of position. And now we have our periodic potential, like so. And how do we model the spring? Well, this is going to be the potential energy V. How do we model the spring? Well, the spring has a linear force. The force is proportional to the displacement, which means the potential is quadratic in displacement. So this is the potential of a spring. This is what the spring does, and this is what the substrate does. And what we need to do is we need to add these two together. So what that means qualitatively is that the total potential of the system might look something like this. So as we now translate the spring across the surface with some velocity, then you can see that this addition between the fixed substrate potential, this one is fixed, and this spring potential is moving, you can see that this will lead to a time-varying potential for the object. So let's look now in a simulation what that time variation might look like. Okay, so what you see here is a combination of a spring and a periodic potential, and the periodic potential has been chosen slightly different strength than I'm showing you here. It has been chosen weaker, so that instead of many minima in this total potential, there are only two minima. And what you see happening in the system is that as the particle is moving, the spring tries to pull it across a maximum of the periodic potential. At some point, the atom is released, and it releases energy that is taken up as heat by the substrate. And then the object is pulled towards the next minimum. The minimum disappears slowly. The object is released again, etc. So basically, in this model, we can understand friction as the external force pulling the object over successive maxima. So that's nice. In this model, we can understand why there's heat generated. There's always heat generated when the atom loses this extra energy because it is stuck for a while in a minimum of the potential, which is not the absolute minimum of the potential. And then the moment it's released, it releases the energy that is converted into heat. Now we can have a different situation. So if we make so this was for strong or moderately strong potential. So basically, this was a situation where there are just two minima in the potential, like so. We can make the potential a little bit weaker, and in that case, the curvature of this potential, of the periodic potential, might not be enough to, the curvature in one direction might not be enough to overcome the opposite curvature of the spring. So in this case, we can end up with a potential just slightly distorted, but we have only one minimum. So in the next movie, I will show you what happens when we have just one minimum. In that case, you can see that because there's no second minimum in the system, the object, in this case the tip, follows quite smoothly the minimum of the potential, and no energy is released, no heat is released in the problem. This model, this Prandtl-Tomlinson model, is interesting. If in this model we plot the friction force versus the corrugation of the potential corrugation, so we'll call this the corrugation of the potential U, which is proportional to the normal force for a macroscopic object. And then what we find is, yes, we find a linear dependence. So this is if you want the corrugation or the normal force. What we find is a linear dependence, but only above a certain critical value. So the friction force actually looks like this. It's zero until the potential becomes strong enough. Basically, you can think of this curvature becoming larger than that curvature, and then the friction force sets in. So this is at the nanoscale. And our simple macroscopic friction law would have predicted something with the same slope at the macro scale, something with the same slope at the farthest offset. So we can kind of see that at the nanoscale, the friction was a little bit more complicated. There's a region where there's no friction whatsoever, but then it increases linearly with the normal force. So you can imagine that if I go to macroscopic normal loads, then the difference between these curves, at least fractionally, will be quite small. The difference between these curves, at least fractionally, will be quite small. And so we can see how the law of the nanoscale, explained by this very simple Prandtl-Tomlinson model, approaches the law of the macro scale. So far, I've told you about something very simple, namely when the contact is a single atom. And even making this very simple approximation, we can also already understand why the friction force is approximately proportional to the normal force. Now, in real life, probably there's more than one atom touching the surface. So let's consider a contact area with several atoms, maybe a long chain, maybe just a few atoms. In the case of nanoscale, probably just a few atoms. Several atoms will be making up the contact. So instead of considering this situation with one atom on a spring, which is the single atom case, now let's consider a situation where several atoms make up the contact. So again, here we have the substrate with our periodic potential that is ultimately coming from the individual atoms. But now we will consider more than one atom making up the surface. So in this case, how do we model the system? Well, we think that these atoms are still connected by springs to the microscopic object, but typically these atoms will also have forces between them. So this is my physicist model of what happens when more than one atom touches the surface. Now these are only masses with springs and some simple periodic potential, and yet the situation is quite complex and in many ways counterintuitive. And the first thing that changes compared to the single atom is that now I have the distance between the atoms as a parameter. So if I label the period of the periodic potential as A, and maybe the period of my object, of the atom distance between the atoms in the object as D, then I can have different situations. So one very simple case is when D is equal to A, when the two periods are the same, or in general, when D is a multiple integer of A, and then is an integer. So let's see what happens in this case. Very naively, all the atoms are doing the same thing relative to the surface, so you might expect them maybe to move in exactly the same way. They will all move together, and these springs between them will not stretch. In this case, I can forget about the springs between the atoms, in this simple case that we'll call commensurate. Basically, when the period of the object matches the period of the substrate, the commensurate case, then the atoms are basically, the atoms are at equivalent positions relative to the substrate period. The lattices, the springs between them will not stretch, and it's as if they're not there. So in the commensurate case, what you can see here is as the atoms are pulled across the periodic potential, because of this commensurability condition where D is equal to A or multiple integer of A, basically the two periods are matched, all the atoms are doing the same thing at the same time. So they get pulled, they first stick, and then they all slip at the same time. And you can imagine, and you can kind of see visually in this case, that the friction is the same as the single atom friction multiplied simply by n. So this is just the single atom friction that we have seen before, multiplied by just the number of atoms that makes up the contact area. Now there's a different case, which we might call incommensurate, where D is not equal to A, and D is not an integer multiple of A. So maybe D could be 1.5A or 2/3 of A or some other number. And what is the most incommensurate case that we can imagine? Well, the most incommensurate case between for D and A is that the ratio of D and A is an irrational number. So an irrational number would be something like square root of 2, or for our purposes, it turns out that the most irrational number in mathematical sense is 1/2 square root of 5 plus 1. This is the so-called golden ratio.
Golden ratio.
The ancient Greeks believed that it had magical properties. For instance, when they built the temples, the two sides of the temples, the two sides of the rectangle, were related by this very strange number, the so-called golden ratio. It is assumed to be aesthetically very pleasing. Now, mathematically speaking, the golden ratio is very interesting because it is the most irrational number in some sense that you can devise. Now, we can choose such an incommensurate ratio of D over A and see what happens in this case. So you can see here that in the case of an incommensurate ratio, the behavior of the transport, the behavior of the motion of the object changes dramatically. Instead of all the atoms sticking and slipping together like we had in the commensurate case, now the atoms move one by one. Basically, the first atom moves over the barrier, the spring stretches, which allows, which facilitates the motion of the next atom over the barrier, the next atom, and so on. So these atom chains move like a caterpillar. They essentially move one by one. In technical language, we call these things kinks. You can see that there are periodic compressions, there are compressions in the chain and stretches in the chain. And so these atoms move like a caterpillar. And now, an interesting fact is that in this case, friction is dramatically reduced. And depending on which regime you are, the friction can even disappear altogether at the nanoscale. The reduction was so large that some people have even coined this with the word superlubricity. Interestingly enough, even though this is a very simple system, just if you want balls and springs, this superlubricity was only discovered in the late 1980s, even though we know all the physics for more than a century. So you can see that just a tiny rearrangement of the atoms, not to be any more commensurate with the lattice, but to be incommensurate in terms of an irrational number, can change friction properties dramatically. In fact, there was a French scientist called Aubry that first pointed out that there's a very interesting transition that happens in the system of a periodic potential and atoms connected with springs when you choose as the ratio between these two length scales the golden ratio. And this is called the Aubry transition. So far, we have considered only, if you want, the mechanics of the motion, which is equivalent to saying if you assume that the system is at temperature T equals 0. Basically, the atom remains at the minimum, it doesn't wiggle around because of temperature, and we have derived the friction loss in this limit. Now what happens for finite temperature? By finite meaning the temperature that is larger than 0. But if you think back of our simple single atom model of friction, where maybe an atom is stuck here as the potential is moving with some velocity v, then in the 0 temperature limit, this atom would only be released at a time when this minimum actually disappears, and then it would have a high energy and it would dissipate this energy to be cooled to the next minimum. However, if you have a finite temperature T, some temperature scale T, that means that the energy of the atom in the potential is not 0, the kinetic energy, but the atom has a smeared out kinetic energy and potential energy that is like so. So what that means is that the atom can thermally hop over the barrier and find the new minimum without actually having to be pulled over this maximum. So what we expect is that temperature effect might reduce friction. So people call this thermal lubricity. The effect that when you heat up the surface, and in many instances you would have to substantially heat up the surface, then friction is reduced because the atom can find the new minimum of potential without actually having to be pulled over the barrier. So let's see in a small simulation what that might look like. You see here is now that the atom has a chance of hopping between the two minima back and forth, and it has a certain probability to be found at either one of the two minima, which is indicated by the size of the red circle in this case. So you can see that when temperature is present, then the atom can follow the minimum locally, the absolute global minimum, simply because it can hop back and forth between the area without actually experiencing much friction. So, in particular, the limit when the temperature is very, very high, or the velocity of the atom is very, very low, then the atom will hop many times back and forth between the two minima, and the distribution between the two minima will be simply given by the Maxwell-Boltzmann distribution, which means that the atom will be predominantly found in the global minimum and will just be following the potential along, and the friction, the temperature, and the friction in the system will be quite small. So in this case, if we do a measurement of friction versus velocity in a simulator that we do, then this is what the result might look like, or what the result does look like. We see here different ranges of friction. We see a range where the friction does not depend on velocity at all. It's zero, friction is zero. Then there's a range where the friction increases with velocity, but only very weakly logarithmically. Please notice that this is a logarithmic scale for the velocity. So the velocity here changes over 5 orders of magnitude. So friction increases with increasing velocity. Then there's a range where friction is actually independent of velocity, just like this simple macroscopic law would predict. And then it turns out when you move the atom very, very fast, then it basically doesn't have time to dissipate all the energy, and friction is reduced again effectively because the atom is hotter. So we can see that the simple macroscopic law of friction only applies in a region which in this experiment was relatively narrow, of relatively low temperatures. So let's summarize what happens to the laws at the macro scale. So the first law at the macro scale was that the friction force was proportional to the normal force, and we found that at the nanoscale, actually what happens is a displaced curve where there's no friction in a certain region, and then the friction follows parallel to the macro result. So this will be the actual friction at the nanoscale, and we see that it's a fairly good approximation to the macroscopic friction, but with a small offset. Our second law of friction was that friction is independent of surface area, of contact area. Basically the idea that a high object and a flat object of the same mass experience the same friction, and we see that at the nanoscale, it's replaced by a much more complicated law that depends on the arrangement of the atoms, or on, if you want, commensurability. So we have non-equivalent arrangements of the atoms that can either lead to large or small friction, and somehow the macroscopic law is some kind of average over these behaviors if we allow for randomness in the positions of the surfaces. And finally, our third law, that at the macroscopic scale, friction is independent of velocity. We found, at the nanoscale, that this can be true, but it is generally true only in some finite temperature range. Namely, that if you move the object very, very slowly, then thermal excitations allow you to always find the global minimum, and friction disappears, the effect called thermoblicity. So one can see that there are nice connections between the nanoscale and the macroscale, but many open questions remain, in particular concerning the point 2, which is that friction is independent of the contact area. What does the contact area really look like between two macroscopic objects? And how is it that this independence on the surface area, or at least on the apparent contact area, actually arises from the properties of friction at the nanoscale?
Very good video, very, very good video.
Let's consider the following problem. Suppose we have an inclined plane, and on this inclined plane we have a block, and down here at the bottom of the inclined plane there's a little bumper. It can be a spring of some type.
It helped me understand friction more, and now we can move on, I guess, which is pretty good. Whew. 12, 14.
And what we have is the block is sliding down the inclined plane, bouncing off the bumper, and sliding up the inclined plane. And what we'd like to do is find the acceleration of the block for both cases. So when it's sliding down, let's do an analysis on that motion. Well, the first thing we have to do is, again, identify our system. In this case, just the block will be our system. So we'll put in the block as our system, and now we have to analyze the forces on the block as it's sliding down. There is a friction with a coefficient UK, and so we have the gravitational force, mg. We have a normal force of the surface on the block pointing up, and because the block is sliding down, remember that our friction force is opposing that motion. Now, when you have a free body force diagram, we have to decide how should we choose our coordinate systems. What we want to encourage you is not to choose a coordinate system, unit vectors horizontal and vertical, just because that's the way one always does it, but to use the constraint of the system to help you choose the coordinate system. Now, a technique for doing that is to draw what you think will be the acceleration on your sketch. So I expect that A is going to go down the inclined plane. That's taking into account that there's no motion perpendicular to the inclined plane. This, drawing the acceleration, remember acceleration is not a force, but this gives me a clue for how I should choose my unit vectors. I'll choose them so that I hat points down, and so I essentially have a one-dimensional motion, and I'll choose j hat pointing out. Now, I'll introduce an angle theta. That's the same angle theta here. And one has to be a little bit careful in doing these types of sketches, but this is also the angle theta. And now I chose a coordinate system, unit vectors. I've indicated relative angles, and the rest of the problem is just vector decomposition in applying Newton's second law. So we'll write down F equals ma, and I'm going to indicate a D for we're talking about the acceleration downwards. And we have two directions to analyze, the I hat and the j hat directions. So in the direction tangent to the surface, we have a gravitational force downward, mg sine theta. We have a kinetic friction force opposing that motion, and that's equal to MAD, where AD is the x component of the acceleration. In the vertical direction, we have the normal force minus mg cosine theta, and here's where our choice of coordinate system helps us. The constraint of the system is that AY is 0 when we choose y to be a perpendicular direction, so this side is 0. Now I look at this and I see A, F, and N, and that's only 2 equations and 3 unknowns, but now I have a force law for my friction, which is that the kinetic friction is equal to a coefficient ukn, and I can see from this equation that's uk mg cosine theta, and now I'm in position in which to substitute my friction into this equation and solve for the acceleration. Notice the mass will cancel, and what I get is that the acceleration going down is just equal to g times sine theta minus mu k cosine of theta. And so that's how we can analyze the acceleration when the block is sliding down. Next, we want to analyze the acceleration when the block is going up. Now, when you have a case like that, it's sometimes easier, again, just to draw. We'll still choose n. Now, the interesting thing is, which way is the acceleration pointing? Just because the block is going up, the acceleration is still pointing down. How do you know that? Well, we'll see that when we analyze the forces. So we still have n, we have mg, but now the crucial point is this is going up. The crucial point here is that the kinetic friction is always opposing the motion, so when the block is sliding up, the kinetic friction is down, and all that we have is a sign change here. This is now plus. So if I choose my I hat and j hat in the same direction, notice both of these forces have a positive component in the I hat direction, so the acceleration will be down, and rather than do all the algebra, all I'm doing is changing the sign, and I get that a up is equal to g sine theta plus mu k cosine theta. And although it may seem slightly counterintuitive, that the acceleration as the block is going up in magnitude is bigger than the acceleration as the block is going down, and that's because of the direction of the kinetic friction force. One of the big difficulties students have in a problem that involves many objects is to successfully identify third law interaction pairs. So today I'd like to look at a problem which shows us how to think about that. So what we're going to look at is third law interaction pairs. Now the problem I'd like to consider is the following. Suppose we have a block 1 and another block 2 sitting on block 1 on a surface, and our surface has friction, and I'd like to push block 1 with a force F. And now I'd like to use Newton's second law to determine what is the maximum force I can push that block 2 will not slip. So I'm trying to find F max such that block 2 does not slip. Now, how do we even begin to think about this? Well, the first thing that we have to decide is when we apply Newton's second law, our first question will be, what is the system that we'll choose? And in this problem, there are 3 separate ways to think about this, just to show you an example. So system A will be block 1, system B will be block 2, and system C will be blocks 1 and block 2. And given these different systems, I can address different questions, and we'll see that as we develop this. So let's start with block 1, and let's look at, we'll start with breaking our problem down into blocks 1 and block 2. And let's draw the free body diagrams on those blocks, trying to identify action-reaction pairs. So let's begin with block 1. First off, we know there's gravitational force, and the Earth is the other pair there, which we're not drawing. There's friction between the surfaces. So there's a friction between the ground and block 1. There is the normal force of the ground on block 1. Block 2 is sitting on block 1, so there's a normal force of block 2 on block 1. And finally, as you push block 1, there's a friction force between block 2 and block 1 that's opposing the fact that block 1 is being pushed forward. So we have a friction force here between blocks 2 and 1. Now this friction down here is kinetic, but if the blocks are moving together, this friction here is static. So those are the free body force diagrams on 1. I'll choose unit vectors in a moment. Now what about 2? So let's draw 2. Well, again, M2G, the Earth, is the other element of the interaction pair. And now block 1 is pushing block 2 up. So we have block 1 pushing block 2 up, and notice our indices make it very easy to see that our first Newton's third law interaction pair is the normal force of contact between the 2 blocks. Now, what else? Here's the subtle thing, is that this whole system will move to the right. What's the force that's making block 2 move to the right?
Friction.
Well, it's static friction. So static friction from block 1 on block 2, this is the static friction, is causing block 2 to move to the right. And now we can see, again, our third law interaction pair. So in this problem, we have 2 third law pairs, this one, and I'll connect the line there. And those are the third law pairs. Now, we can call these, we know by the third law that they're equal opposite in magnitude. We can identify F, we can call this one N, if we want, just to save ourselves the problem of writing a lot of indices. Once we've done that, we're now ready to apply Newton's second law. We haven't yet figured out what the condition is that it will just slip. We'll get to that. But for the moment, we can now apply vector decomposition. So we need to choose some unit vectors. Because I'm pushing the system this way, it makes sense for me to choose my I hat to the right. So here, I'm going to choose I hat 1 and j hat 1. Now, over here, I can choose the same unit vectors, even though I'm thinking about this as a completely separate problem with its own coordinate system. And I'll choose I hat 2 and j hat 2. But because these unit vectors are in the same direction, they're equal. And they're both moving in the positive I directions. And so I expect both A1 and A2 to be positive. And now I can write down on block 1, I can write down F1 equals M1 A1. And because we have 2 different directions, I'll separate out. I like to call this my scorecard. And now I look at the forces. Oh, I missed the pushing force. But that's an interesting exercise. When I looked at this diagram, I saw I had 2 forces going this way. I had no force acting that way. I went back, I checked my free body diagram, and recognized that I forgot to put F in there. Always a good exercise to double check your free body diagrams before you apply Newton's laws. So now, in the x direction, we have the pushing force minus the static friction, minus, we'll call this Fk, minus the kinetic friction, and that's equal to M1 A1. Now, in the vertical direction, we have the ground friction and ground 1, minus block 2 pushing down on block 1, minus the gravitational force, and there is no acceleration in that direction. And I double check my free body diagrams, I check my signs, and that looks right to me. Now, for block 2, I'll apply the same analysis. F2 equals M2 A2. Separate out my 2 unit directions. Notice, even though these unit vectors are the same, I'm emphasizing that I'm talking about block 2. I could have chosen different coordinate systems if I want. Now I look at my free body diagrams on block 2. I see that its static friction is the only one in the positive i-hat direction. So I have F equals m2 a2. And in the vertical directions, I have that my force between the blocks, the normal force between the blocks, minus gravity is 0. And now I'm in position to talk about what is the maximum force. If I push F harder, as if I push F and the blocks go together, the accelerations are the same. I push F harder, the accelerations are the same. I push F harder, and I push F so hard that the static friction is no longer reaches its maximum value. And if I push F harder than that, I will not have, the static friction can't get bigger, and blocks 1 and 2 will start to slip relative to each other. So my no slipping condition is that I want two things. A1 equals A2, we'll call that A, and the maximum force condition is that F static is equal to maximum value. Now, what is the normal force between that we refer to in our friction law? There's two normal forces, the ground and the normal force between the surfaces. But the static friction that we're talking about is between the surfaces, so that's why we use N here and not N ground. And now I can solve for this F max. By the way, we also have the condition that Fk is mu k. What normal force are we talking about? N, which we've called N ground 1. And now I look at my equations, and my goal is to solve for F. I know Ng1 from this equation, it's just equal to M1G plus N. I know N from that equation, so Ng1 is just the sum of the masses times G, so I know this. I have F, which is M2A, and I can now apply my result. So what we'll do is we'll solve for the A's, A1 equals A2, in terms of F max. So over here, we have that A is F over M2. That's from this equation. And now I'll substitute A1 is equal to that. I'll substitute that there, and I get that F max is going to be equal to Fk plus F static max. That's that one, plus M1 times A1, which is F static max divided by M2. And so I get that F max equals, now I'm going to substitute in all of these values. It's going to look a little complicated, and so I'd like to have a little space here for that to get everything in here. And we'll see that it's equal to mu
That's
k
a little space.
M1 plus M2G, Fk mu k plus M1 to MG, plus F static max times 1 plus M1 over M2, but F static max is mu n, and n is M2G, so I get M2G times 1 plus M1 over M2. And there is, if I push any harder than that, block 2 will slip with respect to block 1. Again, all of our terms have the dimensions of acceleration. This is dimensionless 1, dimensions of acceleration, and we did miss one little thing. We missed the coefficient of static friction. And there we have it. Tricky problem. When we analyze the problem about putting two blocks along a frictionless surface and pushing one and asking what is the maximum force such that block 2 does not slip, we have three different systems, and now I want to focus a little bit on what would happen if we just naively chose our systems as both blocks together. So let's try to look at the types of issues that come up when we do that. So once again, let's draw free body diagrams. Now, we begin, we're pushing block 1 with force. Gravitation is the sum of these two forces because our system here is block 1 and block 2. What about normal forces? Well, the ground is acting on block 1. And now here's the significant thing. What about all of those forces between blocks 1 and 2? Well, the forces between blocks 1 and 2 are internal forces. And we saw that they were friction forces, F12 and F21. This was the friction force between the two blocks on block 2 due to 1, and the friction force on block 1 due to 2. There were normal forces between these two blocks, but these are interaction pairs. And the sum of them are 0. And so we see that they're all internal forces for Newton's third law interaction pairs, and the vector sum of them are 0, and that's why I don't need those internal forces on my free body diagram. If I were to draw them, I would have different arrows. For instance, I would have that arrow F21, and I would have the arrow F12, and you can see that the sum of those cancel. I would have the arrow N21, and I would have the arrow N12. Arrows in opposite directions, the interaction pairs sum to 0 because they are internal forces. And again, this enables us now to just draw F equals M1 plus M2 times the acceleration of the system. And so we have our I hat and our J hat directions. Let's pick I hat and J hat. And now we didn't include the kinetic friction force of the ground in that system, so let's make sure that that's there. And what we have is F minus F kinetic equals N1 plus N2 times A. And in the vertical direction, we have N ground 1 minus N1 plus N2G equals 0. That gave us our same result before. Notice that F equals Fk plus N1 plus N2G. We know this is mu k N1 plus N2G plus N1 plus N2G A. So we have the acceleration of the system depends on the force mu k N1 plus N2G divided by M1 plus N2. But notice, because our static friction is an internal force in the system, it never shows up in Newton's second law, so we were never able to apply the condition that F static max was mu static N, what we call the normal force between the blocks, and so we were unable to figure out what is the maximum force. All we can say is if I push F, that's the acceleration, but I cannot determine what maximum force will cause block 2 to slip with respect to block 1. So when you pick your system like this, it's very quick to calculate A, no problem about that, but I am not able to answer any questions that require some type of information about the internal forces. So the art to choosing systems and free body diagrams is to think about the types of questions you're asking. If you have a question that involves something about a maximum condition on static friction, then you want to make sure that static friction is an external force to your system. If it's an internal force, like in this case, you will not be able to apply that condition. Let's consider what we call the window washer problem. What we have is suspended from some ceiling, we have a pulley, and the pulley is suspended by a rope, which we're going to call this string 3, and we have a rope that is wrapping around this pulley, and then it wraps around another pulley. So this rope is going around another pulley, and it's fixed to the ceiling, and this is what we're going to call string 1. And then this string, there's another string that comes down to a platform, and this one we're going to call string 2. And sitting on the platform is a person. So we have a person sitting on the platform, and that person is pulling the rope down. Now, this is a very complicated problem, and it's a classic example of how do we choose systems so that we can apply Newton's second law. Now, one of the important things we're going to do is learn to see when we choose a system, what forces are internal and external, and that will enable us to pick a very nice system which will make the analysis easy. The way we'll do this is we'll approach it in stages. We'll first focus on the person, the platform, and this pulley. By the way, this is pulley A, and this one is pulley B. And let's use the symbol P for the platform, and we'll call this a washer person, and we're going to use the symbol W for the person. So what makes this problem complicated is all these different elements. Now, the first stage is that what we're going to do is we're going to separately look at the person, the platform, and then combine them into a system of person and platform. But notice the rope is connected to the platform. So the next stage is we'll also consider a system consisting of pulley A, person, and the platform and the washer. Now let's draw the free body diagrams. Let's begin by drawing the free body diagram on the washer. So washer, what do we have on the washer? The first thing to think about is the string. The washer is pulling the string down, so the string is pulling the washer up. So that's a force of string 1 on the washer. Now, there's also the gravitational force and washer G. And what we also have to consider the fact is that the person is sitting on the platform, so the platform is pushing the person up, and we'll call that a normal force on the washer due to the platform. And those are the free body diagram for the free body diagram on the washer. Now let's focus on the platform. So here we'll draw the platform, and now let's look at the forces on the platform. Let's begin by looking for the internal forces, the Newton third law pairs. The platform is pushing the person up, the person is pushing the platform down. So we'll write that force as N on the platform due to the washer, and immediately let's just circle this third law pair. Now, string 2 is pulling the platform up. So let's draw that force. We'll call that a tension force in the string. It's on the platform due to string 2. And finally, we have the gravitational force on the platform. And that's our free body diagram on the platform. Now, you may have said, well, why should I separate these out? Why didn't I just use the person and the platform? So let's draw that picture. So now imagine underneath this is a system consisting of the person and the platform. And I'll just draw that system like that. So what we're doing is we're taking these two separate free body diagrams and we're going to combine them here. And by Newton's third law, all internal forces should cancel in pairs. So now let's separately think about the forces and see that that's the case. Well, we have the gravitational force on the system, which is the mass of the platform plus the mass of the washer times G. We still have the string pulling the person up because the person is pulling the string down. So we still have the force F1 on the washer, that's string 1 on the washer. And we still have the pulley, the tension in string 2, pulling it up. So we still have the force T2 on the platform. Now, when you look at this, what we're doing is we're adding these two free body diagrams together. The internal forces now are the normal force. They're equal in magnitude, opposite in direction. So when you add them together, they cancel, and we're just left with that, with that, with that, and with that. And so this is now the combined system. Now you might ask, why did we not include the pulley? Well, let's take a look at that. So I'm going to draw the free body diagram just on pulley A. So let's draw pulley A. Now, what we have here is the string on both sides is pulling pulley A up, and that's the tension in string 1. So what we have is I'm going to call that tension in string 1, tension in string 1. And just to alert you that keep in mind that this force here is the force of the string on the person, and this too is also tension in the string because this is our assumption of a massless string. So notice that everywhere in the string, the tension is uniform. So I'm just going to simplify that by calling it T1. What are the other forces on the pulley? Well, we're assuming that these pulleys are massless, and so there's no gravitational force on the pulley. And the only thing we have is the string pulling, there's a tension in the string. So now this is a little bit different. This is a force on the pulley too. So at the moment, let's do something a little bit different. Let's consider our system to be the string, so it's pulley A. We call that string 2. That's our system. So I modified that a little bit. I just didn't consider the pulley separately. I considered the pulley and the string as the system. Then here, the string is pulling the platform up. The platform, therefore, is pulling the string down. And once again, we have a third law pair. And so if I added these two together, then what I now have, and this is why this problem is kind of complex, we have pulley A, string 2, platform, P, and washer, person. And if we now add these two systems together, we have this complicated system. But what are the forces on this system? Well, the rope is pulling it up. The person was, remember, we had this force, W1, was the force of string 1 on the washer. That also was the tension everywhere in the string. So we have another T1 up. these two forces now cancel in pairs, the internal forces there. And so down we just have mass platform plus mass of the washer times G. And so you see in this problem, if we tried to treat everything separate, and I could have even had the string separate, I have a lot of free body diagrams, but when I think about what's internal and what's external, I can take these two pieces, combine them here, internal forces cancel in pairs. I can draw these two separate systems, again, combine them, internal forces cancel in pair, and now I have this pulley A. Now I can write down Newton's second law. So what I'll do next is I'll introduce, I still have to consider pulley B, I'll use this as my system, and I'll write down Newton's second law, and we'll be able to solve this problem. So now that we've combined pulley A, string 2, platform, and washer as our system, we can now address our question. If we measure the acceleration of the person, what is the force that the person pulls the rope down with? Well, of course, that would just be the tension in the string, and with this simple system, we can now apply Newton's second law, F equals ma. But recall, we need some directions, so suppose we expect that the acceleration of the platform in person is up, so we'll choose a unit vector j hat in the positive direction, and now the problem becomes tension 1, 3 different tensions, 3T1, and gravitational force minus mp plus mw times g. Now, what is the mass that we have to consider? Again, what is the mass of our system, of the platform and the person, and we assume the pulley and the string 2 were massless, so we have simply mp plus mwa. And so we can now solve for the tension in the string, which is equal to mp plus mw times g plus a divided by 3. And recall that this tension that the string is pulling, this is what we call the force that the person of the string on the person, and by Newton's third law, that's also on the washer, that's also the force that the washer applies to string 1. So this was our goal. It's the force that the washer applies to string 1 by the third law. And so by thinking about how to choose a system, what could be a very complicated problem with lots of equations is simply one equation.
Where do forces come from? All forces arise from the interaction of two objects with each other. In this example, we have two objects, 1 and 2, interacting with each other, in this case because their surfaces are in contact with each other, one sitting on top of the other. And the interaction between the two objects gives rise to a pair of forces. I have one force that's acting from object 2 down on object 1, and the other force that's acting from object 1 back up onto object 2. And these forces, following Newton's third law, are equal in magnitude and opposite in direction. What if we now push these blocks horizontally in opposite directions? At their interface, there is a frictional interaction. This interaction gives rise to a pair of frictional forces that are parallel to the interface. The friction force on the top block from the bottom block is opposite in direction but equal in magnitude to the friction from the bottom block due to the top block. Let's look at some of the common misconceptions about forces. First of all, motion is not a force. If I have a block that's moving at a constant velocity along a frictionless plane, then there's no horizontal force that's acting on this block because there's no interaction that would give rise to a horizontal force. The fact that it has a velocity does not necessarily mean that there is a force acting on it. Another common mistake is to think that forces transfer through objects. For example, if I'm pushing a book against a wall, it might seem like the force from my hand is being transferred to the wall, but what is really happening is that there are two independent interactions. The interaction of my hand with the book and the interaction of the book with the wall. And these are separate interactions. The forces might happen to have the same magnitude in some cases, but it's not because the force from my hand is being transferred. Forces arise between pairs of objects, and those forces can only act on those two objects. Let's look more closely at Newton's third law. So Newton's third law says that when there are two objects that are interacting, there will be two forces that arise from that interaction. And these two forces are always equal in magnitude and opposite in direction. These two forces, this Newton's third law pair of forces, never act on the same object, but instead one force acts on the first object and one on the second. Because these forces arise out of the same interaction, they have to be the same type of force. So they could be gravitational forces, frictional forces, normal forces, etc. Let's look at an example of a book sitting on a table. It's being pulled down by the gravitational force, and it's being held up by the normal force. Are these two forces a Newton's third law pair? The book is not accelerating, so these forces are equal in magnitude and opposite in direction, but they cannot be a Newton's third law pair for two different reasons. First of all, they both act on the same object, the book. And second of all, they arise from different interactions. The normal force on the book is part of a Newton's third law pair that comes from the interaction between the book and the table. What's the Newton's third law pair of the gravitational force on the book? Well, because the gravitational force arises from the interaction between the book and the Earth, the other force in the Newton's third law pair is actually the force that the book exerts on the Earth. You might not think about the book acting on the Earth, but the force is actually equal and opposite to the Earth's force on the book. It's just that the Earth is so much more massive, the force has no detectable influence on the Earth's behavior at all. Newton's second law states that the sum of the forces on an object is equal to the acceleration of that object times the mass. But what if instead this object is actually two objects? Do I now need to consider the forces that are acting between each of these parts? Or what if I consider the object to be made out of even smaller parts? I can take it down to its smallest components and consider the interactions between all of the atoms in the object. This seems like an overwhelming number of forces that I'm going to need to calculate just to find the force on this object, but I never seem to calculate this many forces. Why is that? All of these forces between the atoms and the object cancel out because they are Newton's third law pairs. If both objects are within the system, since a Newton's third law pair of forces is equal and opposite, the total force is just zero. We call these internal forces. That is, forces that are acting between a pair of objects that are both within our system. On the other hand, external forces, forces that act on an object within the system by an object outside the system, are what we need to consider for our calculation. We could be more precise about Newton's second law and say that the total external force on the system is equal to the system's acceleration times the system's mass. Let's look at an example of how the selection of a system will affect the forces that we need to consider. I have 3 blocks, I'll call them 1, 2, and 3, and a force that's pushing block 1 to the right. We'll first take a minute to look at notation. We will write the forces as F1, 2, and this means that it's the force exerted by an object 1 acting on an object 2. In this example, I have pairs of forces between each block. the interaction between blocks 1 and 2, and the interaction between blocks 2 and 3. Let's look at the internal and external forces on the system if my system is made up of block 1 and block 2. I have this external pushing force, F external, that's acting from the external pusher on block 1. Blocks 1 and 2 are interacting with each other, but these are both within my system, so these are internal forces that I do not need to worry about. And finally, block 2, which is within my system, is interacting with block 3, which is outside my system. The external force here is the force that is acting from block 3 on block 2. Now, we know that the two forces that are relevant to calculating the motion of the system are the external pushing force and F32. If my system is instead made up of blocks 1 and 3, block 2 is now part of the external environment. Can you figure out what the internal and external forces are?
Yes.
In this case, the external forces to the system are the external pushing force, F external, F21, and F23. Let's take an example of using Newton's second law in problem solving. In this example, we'll figure out why riding in an elevator can give you a weird sensation of weightlessness or extra weight depending on which way you're accelerating. So let's say there's a person standing on a scale in the elevator that's accelerating upwards with some acceleration A. So we want to know what the scale reads. First, we need to really understand what the scale measures. The number that it gives you is related to the normal force that you are exerting on the scale. So this is a Newton's third law pair force to the normal force that the scale exerts on you. So if we can figure out the normal force on the person from the scale, we'll know what the scale should read. Now let's set up our coordinate system. I'm going to assign the upward direction to be positive y, and since the only forces in this problem are acting vertically, I don't need to define another direction. I'll pick the system to be the person. Now I'll think about what we know and what we don't. Since that person is standing in the elevator, not jumping, not moving otherwise, they must be accelerating upwards with acceleration A, the acceleration of the elevator. I also know the mass of the person, so now I have one side of Newton's second law. Now I need to think about what vertical forces are acting on the person. First, there's the gravitational force pulling the person down. This gravitational force does not depend on the acceleration of the elevator because the gravitational interaction is just between the person and the earth, so the force is minus mg. Finally, I have the normal force that's holding the person up. This is the normal force from the interaction between the person and the scale, and so this is the unknown quantity that I'd like to know. Let's look at Newton's second law. On the left, I have Fn, the normal force that I'm interested in, minus mg, the gravitational pull from the earth. And on the right, I have m, the person's mass, times a, the acceleration of the elevator, and therefore the person. Notice that when the elevator is accelerating, the normal force and the gravitational force do not have the same magnitude. That is, they don't cancel out. So now I can solve for Fn, and I can find that it's just m times the quantity a plus g. Have you ever noticed that at the bottom of an elevator ride, when you're accelerating upward, you feel heavier? And at the top, when you're decelerating, you often feel lighter? You can see that if I change a to minus a in the...
I have not beaten it yet. It will take me 200 days to beat it. To beat Bachelor Physics. So we're only at the start. Custis Ordano. But eventually I will beat AI. Yeah, see? One more hour for today. And then tomorrow a stream again. And so on 200 days. I'm trying to beat AI in new physics. I'm trying to become a physicist. It's just my way of saying becoming a physicist. Nothing else. I want to become a megalomaniacal physicist. You know? Not the one who's gonna try to unify like gravity and forces. I think that's bogus nonsense. But the one who truly understands physics, and then when I've truly understood everything, I know this. Megalomaniacal. Yeah. Oh, megalomaniac. Yes, I am a megalomaniac. Sorry, tired. Been streaming for 4 hours. I'm not used to this shit. But I will. More scientists should be criminally insane. Listen to me. This is just classical physics. I actually passed this 3 years ago or something. I had a long depression and so on. So I'm getting back. I want to understand it completely. I want to be able to, you know, do the examples, and then move on to thermodynamics, which I also passed, then to electrodynamics, then to quantum mechanics, then also mathematics on the side, and so on until I have done it all. And according to my calculations, it will take me 200 days for bachelor's, everything in mathematics and in physics, and then 400 days for every graduate one I want to do. After that, what should not morally exist? Let me show you something. I'm not just working on this stuff. I'm not. Let's go to CMD. CD, CDC, CD, CD, CD misanthrope. There is no misanthrope. You're joking me, didn't I deleted it. Theoretically, zombie workers are possible. Yes, they are. And AI will be the zombie worker force. CD. Wait a second. I gotta find. Where have I put my stuff? I think it's in C. Oh, no, it's in D. It's in D. CDD. CD. Misanthrope. Metareason. Wait a second. When you forget where you put your files. Let me see. Fanboy game, no. Fanboy TV, no. Bitcoin, no. Misanthrope is here. In CD. What CDD? Realistically, I'll take it is a lot of little jolts of electricity and an algorithm to move the body, but it will possibly create a sort of new disease. So I can just do it. Yeah, you can try. New corona. Aha. C D. Misanthrope. Cargo run. Look at this. It will take a while to start. Okay, look at this. It's a red window. Very appealing, isn't it? But the truth is, this red window is full of fractals. See, I'm making a game with Ray Martin. This is my project. So I'm not just doing this. Let me minimize so the FPS is okay. I have not done more FPS stuff. Yeah. You see, I had some lag spikes there. Doesn't matter. Let's go back to physics. Yeah, the stream was bugging out because of my program. I fucking... I'll show you the screenshots. Wait a second. Screenshots. Screenshots. Look at this. A fractal. I made them. A fractal. I have no idea why I made this. This is actually a Mandelbrot in 3 dimensions. and many more. How big is the fucking program? It's not the problem that the program is big. It's not the problem that the program is big. It's the problem that ray marching is expensive computationally. So I haven't really optimized it yet. But nice of you to come, Casto Sordano. Ah, evil scientist. Indeed. You can look at my YouTube videos. You'll find how fucking evil I am. I made a Dogecoin robot that goes onto my breasts and plays the currents of the market so I can understand it. Blow smoke at you. Let me see what else. What else is there to show? Yeah, look at this. This is a well-known scientists when they discovered this fractal. They thought it was not interesting enough. Yeah. That is the second worst thing you could do to a device attached to your breasts. But I did it. And I recorded a YouTube video like 3 years ago or something. And I'm trying to become more, how do I say this, productive. So I will be productive. There will be no laziness going on, depression going on anymore. No, this looks familiar. Oh, you probably saw it because I put it in one of my YouTube videos or something. I don't know. But it's beautiful. It's so beautiful. And look at this. I started a program which renders it, but it's too strong for streaming. I will continue to make strange things with my science powers, but you must admit I must learn science as well. It's been too long that I've just gathered information and toyed. I want to become a real scientist, one that can change the world for the worst. For the worst. Yes, a megalomaniacal scientist. Where are you from, stranger? F equals ma. Beautiful. You know, Newton taught about how if the apple falls, why doesn't the moon fall? And that's what led to his laws. America. I plan on going there one day. I mean, I was there in New York in 2019. But after that, not so much. I really like America. I wanna live there. It's my destiny, I guess. extreme FPS and so on. But yeah, I love fanboys. Fanboys are the best. A fanboy connoisseur, you might call me. I'm from Serbia. Nothing can destroy America. It's gonna become a global superpower. It is gonna be a global superpower based on every trend throughout the century. The only thing that can kill America is itself, and by that I mean if they let AI loose, if AI becomes smarter than us, and then, well, then we're all fucked. You have not seen anything. The 21st century. You have not seen anything. What has it been? 25 years, and I have not even lived those 25 years. I lived 24, 23. I'm 20. Yeah. Sorry, brain busting. Trust me, there is no collapsing America from the inside. No collapsing it. I can bet my money on that. China will collapse. It's the demographic curve is all over the place. I don't care about Donald Trump. I don't care who sits on that throne. It's irrelevant to the grand schemes, to the means and that fucking person is autistic. Very nice to talk to you. I mean, amidst the physics. What brought you here, even? Was it the title? I know it was Elon Musk. Elon Musk basically bought the election for himself. He's gonna use that for deregulation for his companies. I'm not stupid. The fanboy tag. Oof, you might be sorely disappointed. I'm currently having a beardy and am a pretty fat fanboy. But I am a fanboy nonetheless. You'll see. You don't have to judge. Yeah. I did not have a turbulent life. Only depression and mania. I'm bipolar. I mean, that's obvious from everything. I post once in a lifetime and so on. But do you know what I got? I got the invitation to the Elden Ring network test, and I have 2 more friends, and we're gonna be playing that on the 14th to the 17th like crazy. I think I cannot stream it. I think I cannot stream it, but Jesus, do I love Elden Ring. Elden Ring is like the best game ever. All my saves are gone, So it just says 800 hours played, nothing else. And that's not even including mods. Custo Sordano. Custo Sordano. This is Mise en Trash. I think it shows well on camera. Let me see. Boop. Mise en Trash. I'm not Mise en Trash. This is Mise en Trash. My god. Born on the 5th of December 2018, I created him. I'm a megalomaniacal person. Yeah, you should play Elden Ring. Elden Ring is amazing. Truly one of the best games ever made. Like, what is it? It's a god without powers, and a god you can test his godhood. You see, I say this is Mise en Trash. He has no powers. That's it. He's even blind, even though he has these little thingies. Those are not eyes. He cannot see. It's a strange bread thing. No, it's made from polyurethane. And every 5th of December I celebrate it with people. I celebrate his birthday. My god, that was lookable. Trust me, that does not insult me at all. I have heard that it's so many things. Some think it's a bomb. One person told me that it might turn out one day that I'm Satoshi Nakamoto, the creator of Bitcoin, and it will be inside of Mise en Trash that the 1 million Bitcoins are actually hidden. Who knows? Maybe that's the case. But yeah, I'm finally a bit happy. I've been making videos, streaming, World of Warcraft, Fanboy Dinosaurs. How did I get it? How did I make it? Well, with one day I was totally clear of mind, no drugs, nothing, I promise you. And I was like, time to create a god. Time to lay bare my beliefs, if they can be called beliefs. I'm pretty scientific, so I created my own thing. And this year 15 people came to his birthday. 15 people. It's a lot of people. Mise en Trash. His name makes no sense to mortals or me. Trust me, that was 2018. Man, I was 17 years old. Meaning, yeah, no drugs. He got forged by polyurethane foam like this, like shh, and then put some glass onto him and some meta materials I created in my mad science phases. Let me show you some stuff I have around the room. First, well, obviously, I'm the creator of this. Look at Miyazaki. Beautiful. Beautiful. My man. But also this. Wait a second. This is the coin of Mise en Trash, and I'm showing it first to you. It will be featured in You need a large brick of titanium for undisclosed reasons. You can order some. I need to reforge Mizuntaresh, and I need a lot of graphene for that. But look at this. The coin of Mizuntaresh. One side is me. It's literally me. This was my face casted in. You can even go into the mouth. That's the nose. Where's the mouth? Here's the mouth. And the other side, a god. Let me try it. It's why I didn't bomb by French midterm. Yeah. Are you studying something? I'm not so um, uh, well understanding of your units or your types of um, school. I know bachelor's, master's, and doctorates, but below that, primary and so on, it's kind of different than here. So yeah. I'm gonna toss the coin. It's really fragile and heavy. Oh. Do I have enough water to drink my meds? I have. Time to drink my meds. Okay. Boop. 1 med. 2 meds. 3 meds. 4 meds. And of course the 5th med. On top of the 2 I already drank today. That's 7. Oh god. Not joking. Ah. You know, be careful with meds, because sometimes doctors prescribe you just vanish one day. Oh, sad. Be careful with meds, because what the doctors prescribe you, some bad doctors, well, they prescribe you like stuff that really destroys you. I used to be anorexic, like really anorexic, like for most of my life, and then I got a med, and that shot up to 126 kilos, and then I lost 26 kilos when getting off of that med in 3 months. Fair. I mean, depending on your problem, maybe you do need meds, maybe you do not. I know I barely feel them. I barely feel anything. This as well. I just decided to smoke, I don't know, 2 months ago, because to calm my nerves, to not use too many meds. Yeah. Yeah, it does that to some people. To me, it had no effect. That's why I'm drinking a horse's dose. Let me see. Damn, I got 108 subscribers. That's a doozy. I never believed Mizuntrash would be followed by 108 people all around the world. Mostly from America. See inches and the real units. I know the feeling. I am and still am lost, but it does get slowly better over time. Basically, what I'm doing here is my last resort to using my power, my only power, and that's my brain. I think and I act on what I think. Very strongly. What else is there to show you? Not much. Oh! I think, but I just couldn't really do anything at first because it was medication for focusing. Oh, ADHD medication. Were you taking speed? Well, Adderall. It's literally speed. Oh. Yeah, ADHD medication. Adderall. It's basically speed, chemically speaking. Yep, that's what it does to your body. Oh. I'm glad to hear that. Very glad. I hope we all help each other in the end. And AI doesn't kill us all, but I hope we all help each other in the end. You know, the fanboy tag is still there because of this. Because of dinosaurs. I was making fanboy dinosaurs. Yeah, you could beat AI in a fight, but not in brain power. See, I was creating Femboy dinosaurs. They're so good. I'm gonna do that for every single species. Maybe tomorrow I do a stream on femboy dinosaurs. Yeah, this is the Murica, Alabamasaurus. This one was my favorite. I mean, beautiful. And this is a Blahio bone structure. This is some Blahio obsessed dinosaur. This is, I have no idea what this is. This is, what the fuck, what was he making? I'm not taking drugs. Cave its servers in with my foot. Well, some powerful people will protect the servers, sadly. This one is good. This one is good. This one is just horrible. This one is Kawaii bone. This one is, well, similar. That's the last stream. I got to 100 dinosaurs. Out to 1600. 1600 dinosaur species. You who Elon Musk? His body's already fucked up. I can just make it worse. Yeah, his body is fucked up. $139 here. It's nice, you know, having a companion on the internet, even though we're in a stream format. Can't really chat. But a break was needed anyways. See ya. Have fun. I think I'm gonna end it here anyways. Dead tired. Maybe you'll like my next stream better. Trust me, there's some content on 8 followers. Is that a lot or a little? Oh, you followed me. That's my my brain being mush now. Thank you for the follow. Thank you very much. I stream here and on YouTube. I read both chats. And I've been streaming for 5 hours, it seems. So I'm gonna end it. Yeah. You too. Have a nice night. See ya.